In this video, we're just going to go over trigonometry. So I want you to understand some of the basic things that are very, very important under the study of trigonometry. And I hope at the end of this video, you'll be able to answer multiple questions from this topic. Okay, so to start with, we are very much aware of what we call the trig ratios, which is also called SOHCAHTOA, right? Okay, so when we're dealing with trigonometry, we're trying to study the relation that is there between our shapes, of course triangles to be specific. So what relationship is there between the angle inside there and the sides? So that is what trigonometry is very much concerned about. Okay, so now the trig ratios apply to what we get to call the right angle triangle, a triangle in which you get to see a 90 degrees. Okay, so we call that a right angle triangle. So the side that is opposite to the right angle triangle, we call it the hypotenuse. It's the longest side in a triangle, in a right angle triangle. And then these other sides, one is called the opposite, depending on the angle that you're looking at. Okay, so let's say we're looking at this angle. That side on the other side is going to be referred to as the opposite, and then this side that is attached to this very angle is called the adjacent side. So that is where all our trig ratios are built on. So if we talk about sine, so the sine of that angle theta is given as the opposite over what? Over the hypotenuse. So this is all coming from this part. So everything else remains the same. If you go to the second trig ratio, it's going to be cosine of the angle theta. Now look at the adjacent side. So it says adjacent over hypotenuse. The other one is to be tan opposite over adjacent. So that can help you to get to find the angle theta in a case where we've given you the sides. You can also get to find one of the missing sides when you're given the angle theta. So we'll get to look at that a bit later. So I've just given you a review on your trig ratios that you are expected to know. Okay, another important aspect that we need to understand are what we call spatial angles. So spatial angles are the angles that you know the actual value. Okay, so for example, we do know that sine 30 is basically equivalent to what? To 0.5. So that's a spatial angle. This is a spatial angle because you know the result even without using what? A calculator. So what we can do is let's try to look at some of these triangles that can help us remember all these spatial angles. So I'll start with a 30-60. Okay. So we have a 30-60. So this would be our 90. And then I can consider this one to be our 30. And then this is 60. So of course you do know that if you get to add the angles in a triangle, it's supposed to add up to 180. So of course 30 plus 60 is 90. This is the right angle, which is also 90, which sums up to 180. Okay, so now the good part about this triangle is that you already know sine 30 is very common, so at least you can know it. Sine 30 is equal to 0.5, right? So 0.5 in terms of a fraction can be given as what? 1 over 2. Now if we go back to our trig ratios, we said SOHCAHTOA, right? The first thing that we had was dealing with sine. So we said it is what? Sine theta being equivalent to the opposite over the hypotenuse. So if we have sine 30 being equal to 1 over 2, it implies we have opposite over what? Over hypotenuse. So our opposite to 30 should be what? Should be a 1. So put a 1 there. So the opposite to 30 should be a 1 according to the trig ratio. And then the hypotenuse should be a 2. And that becomes a 2. So this is the beauty about this triangle. Because if you know 30, you know the trig ratios, you'll be able to come up with the sizes of the sides. And then what about this other side? What can you do? You can use the Pythagoras theorem. Of course, you know the longest side. So the longest side, the square of the longest side, which is the hypotenuse, is equal to these other sides squared, the summation of the squares of the two adjacent sides. So let's say that is x. So assuming you don't know, that is 4, and we'll subtract a 1 equal to x squared. So we'll get our value of root of 3. So that is how you can remember, in case you don't know the actual values, that's how you can remember this triangle. Now this triangle will help you understand a lot of things. So you already know sine 30 at least for the start. So we do know sine 30 is equal to 1 over 2. Okay, what else should we know? So now this 30, if we continue looking at our trig ratios, okay, and then we proceed to the next part, we've already dealt away with the sine, we can go to the cosine. So it's going to be cosine of 30. Now this one is interested in the adjacent side. So in this case, the side that is adjacent to the angle 30 is this other side, this side. Of course, when I'm looking at the opposite and the adjacent, forget about the hypotenuse. So we're looking at that. So root of 3 is what? Is the adjacent side. So say it is root of 3. The hypotenuse remains 2. So we now know that cos 30 is equal to that. That's also a special angle. And then what else can we look at? We can change the angle. Or before even change the angle, we can still continue and look at tan 30. So tan 30, which is like the last part of the trig ratio, is equivalent to the opposite. The opposite is still 1, so it will be 1. And then over adjacent. So the adjacent is still root of 3. So these are the special angles in relation to 30. Okay. So you can use that triangle to help you remember all this. Very, very important and very applicable as you get to look at your equations, especially in assessments where they don't want you to use a calculator, or even a case where you're allowed to use a calculator but then they want you to simplify it or prove identities. You'd want to use these to work out your solutions. Okay, let's try to move. So I hope you've written down this. We'll now go to a different angle. So if we go to 60, you notice that sine 60 to start with. Of course, its opposite side is the root of 3. So we have root of 3. The hypotenuse still remains 2. Again, if we change, say sine, we'll go to cosine. Okay, so cosine 60. So the adjacent side in this case to this angle is a 1. So it's 1. And then hypotenuse still remains to be a 2. And then tan 60 is going to be what? So the opposite is root of 3. And then the adjacent is a 1. So this is just that. Okay, so I'm sure you've noticed one thing. Sin 60 is basically equivalent to cos 30, right? And then sin 30 is equal to sin 60. So you can also know that to help you remember faster. Okay, so these are the major identities from this triangle. Of course, you can talk about 90 as well. Look at the angle 90 itself. So if you look at 90, the opposite is still the hypotenuse. So when you say sin 90, what's the opposite? The opposite is a 2 itself. And then what is the hypotenuse? Still a 2. So sin 90 is basically equivalent to the 1. What about if you say cos of 90? Cos 90 is equivalent to what? So this is a case where now you would want to confuse yourself a bit. Also, you understand when you look at the functions, because when you look at the functions, it will be very much easier, because you know, whenever you're talking about the cosine graph, this is the way it behaves, right? So if you're starting from 0 there, sine 0 is equal to a 1, sine 90 is equal to a 0, okay? And then that is sine 180, which is equal to negative 1, and then, so this is cosine, and then cosine 360 of course is also going to be equal to a 1. 270 is going to be 0. So that will make more sense as we talk about the basic functions. But for now, we are done with this spatial triangle with special angles. We can go to a different one, 45. So this is a triangle where we have two sides having an angle 45. Okay, so let's put our hypotenuse to be down so that we have a right angle on top there. So these sides are going to be 45 and 45. Okay, so what we can do is let these sides be e1s, and then if you try to find the hypotenuse, what are you going to notice? You notice that the hypotenuse is going to be root of 2. Of course, we're saying 1 squared plus 1 squared is equal to the hypotenuse, so you are going to find the root of 2 as your hypotenuse. Okay. So you've noticed that the angles are the same, and then even the sides are also the same. Now the hypotenuse is going to be the root of 2. So we can come up with special angles as well. So sine 30, sine 45, sorry. So if you look at sine 45, if you go back to your trig ratios, so katoa, I'm sure you're able to remember that. So the first part is focusing on the opposite over the hypotenuse. So the opposite is the 1, the hypotenuse is root of 2. If you go to cos 45, the adjacent is still the same 1, and then the hypotenuse is also the same. So you notice that the opposite and the opposite and the adjacent in this 45-45 triangle are the same. So for this angle 45, the opposite is a 1, and then the adjacent is also a 1. So which makes it possible we have this idea to say sine 45 and cos 45 are basically equivalent. Okay. And then what about if you talk about tan 45? So the fact that tan 45, the adjacent and of course we are talking about the opposite and the adjacent, they are the same. So we're going to have a 1. Tan 45 is basically equivalent to a 1. Okay, so these are the major ones that we can talk about under this triangle. So I just hope that now you know the major special angles. That will help us to simplify some of the equations. Okay, so even as we talk about referencing now, angle references, we need to understand the way the quadrants are. Okay, so we'll go to our quadrants. So what you need to understand is that in the first quadrant, all the angles that you get are using a calculator. So you can use a calculator or use special angles. All the special angles that we've talked about so far are in the first quadrant. Okay, so we do know 0, 90, 180, 270, and then 360 there. Okay. So all these are positive. So all angles are positive in the first quadrant. Whether you're looking at sine, cos, tan, they are all positive. Okay. And then in the second quadrant, only sine functions are going to be positive. So all students take calculus. So that can help you remember. Okay. So all students take calculus. That can help you remember. So you can try this out. Try to get any angle between 90 and 180. Let's say 120. So sine 120. Try it with all the functions. Cos 120. Try it with tan 120. You notice that only sine 120 is going to be positive. All these others are going to give you negative answers. That's what we are trying to say. Now, if you try to get any angle between 0 and 90, and then try to use any of the three functions, you are going to notice that they are all going to be positives. Okay, they are all going to be positives. So we already demonstrated that using the special angles that we had, because we are all less than 90, so they were still giving us positives, and that's very, very important for us to understand. Okay, now with this in mind, we also need to understand that if you have this function, I'll start with an example. Let's say you have the angle sine x is equal to 0.5. So this angle x, you already know by now that the angle that you can put there to get 0.5 or 1 over 2, we can use special angles to do that. Of course, for the sake of understanding, what we get to do is we need to find we call that finding the inverse of what we have the other side. You can use a calculator, but that is a special angle. No need of us using a calculator. We know that the angle x is basically equivalent to 30 degrees. Very important for us to understand. Okay. Now, hoping that you've understood that x is equal to 30, in that case, it can give us 1 over 2 or 0.5. I want you to understand that that is not the only solution. Sine being a function has got multiple solutions, a lot of values that you can put there to give you with 0.5. So, well, if we're trying to find a part where we're going to have a positive 0.5, we need to focus where? In the second quadrant, because we know in the second quadrant, that is where sine functions or sine of sine angles are going to be positive, of course. Okay, so what we get to do is let's look at this. So the way we get to find our angles is we'll draw a line there. So just say 180 minus 30. Okay, so I hope you get that. So the basic thing that we can say is whenever we're trying to find an angle in the second quadrant, we just subtract the angle in the first quadrant from what? From 180. That's a basic idea. So if you have 30 there, it implies that 180 minus 30, which is basically going to be equivalent to 150, is also a solution. You can grab your calculator and try that. Sine 150 is also going to give you 0.5 or 1 over 2, which is true. Okay, very important for you to understand that. Now, what about if I change it? Let's say I go to cos, and then I say cos, let me use something different. Let's say x, and then is equal to 30. So now in this case, you will realize now the importance of us knowing the special angles. Okay, so we say the special angles, what value of x can give us. What have I put on the other side? I'm not supposed to put a 30 there. I'm supposed to put 0.5. Sorry. Okay, sorry for that. So what are we supposed to put where is x to get 0.5? So I've already even given you an idea on what you're supposed to do. So obviously the value of x will be what? So if you go to special angles, it will be 60, because we said cos 60 and sine 30 are basically one and the same. Okay, and I hope you are still able to remember the 30-60 triangle to help you remember that special angle. Now, when they give you such a question to say find the value of x, they don't just expect you to find one result. Of course, they're going to even give you the range. Let's say they ask you to say between 0 and 360, find the value of x. So they can say find the values of x. So the second result, you're supposed to understand where do you expect cosine to be positive, because the other side is a positive 0.5. So you need to ask yourself. So you realize that we are talking about what? The fourth quadrant. Now in the fourth quadrant, what you get to do for you to find the angle is you subtract from 360. So it's 360 minus the angle in the first quadrant. And then just to add more, in the third quadrant, we add to 180. So very easy. Never should you think of using 90 and 270. We only use the angles along the x-axis. So if is it before 180, you subtract. Is it after 180, you add. Is it before 360, you subtract. Okay, so that is the easiest way you can remember when you're dealing with a case where you want to find the other solutions to your question. Okay, so that is what you get to do. So in this case, 360 minus 60 is also going to give you 300. So if you grab your calculator, cos 300 is also going to give you 1 over 2 or 0.5. That is the way it gets to work. Now, let's look at something different. What about if you say it's sine x is equal to negative 0.5? So I can also say negative 1 over 2. So now, look at this. It's a negative. Did we talk about special angles that are negative? Of course we didn't. But what we know is, let's try to assume to say we're trying to find the value of x when we have a positive result on the right hand side. So we'll say our possible result if we had a positive 0.5 was going to be obviously 30, because we know sine 30 is equal to 0.5. Now notice that in this question they want a value that can give us a negative 0.5. And now let's say they want an answer between 0 and let's say 360. So going back to our quadrants, we said all students take calculus, right? So in which quadrant are you able to see that sine is going to be negative? Since we said in the first quadrant all of them are positive, in the second quadrant sine is positive, so obviously it's going to be negative in the other quadrants where tan and cosine are expected to be positives. So therefore, what should we do? We said for you to find the angle in the third quadrant, you get to add to 180. And then in the fourth quadrant, subtract from 360. So therefore, possible results of values of x are going to be 180 plus 30, 360 minus 30. So we have 180 plus 30. What do you expect to have? 210. And then 360, that is 330. So these are the values of x, two values of x. Don't present this one as an answer because it's going to give you a positive. So you are just using it to help you find the answers. Because we use reference angles, we use the angles between 0 and 90, which are always positive, to help us find the required results. But in a case where they wanted us to find for positive 0.5, you would agree with me that 30 would also be an answer. But in this case, we've just used it to find the answers to the other parts where we expect sine to be negative. So the same applies to cosine, to tangent, and yeah, so the same applies. So that is the way you get with references of angles. Okay. Now let me just try to show you the way you get to convert between radians and of course degrees. Okay. So you do know that when you think of these quadrants in terms of the radians, so 0, so that is pi over 2, and this is pi. So how about 270? Let's say you don't know 270. So one thing that I use myself to help me understand, because initially when learning my angles, I started first of all by dealing with angles. I came to learn about radians a bit later. So this used to help me. Understanding that pi is basically equivalent to 180 is something that will help you out. So in a case where you want to convert 90, let's say 90, what you just want to do is always just divide by 180. Or let me just say multiply by pi over 180. So you get to understand that this is going to give you 90 into a 90 itself is going to give you a 1, and then you have a 2. So pi over 2. And then what about 270? So 270, all the same, we'll just divide by 180 and then add a pi. Find the ratio. This can divide. 27 can be divided by 9 3 times, 2 times. So this gives us 3 pi over 2 for 270. For 360, of course, we just know we are doubling the pi to give us 360, so it becomes 2 pi. So that is the basic or the easiest way to convert from radians, from degrees to radians. How about from radians? So when you're moving from radians, all you can just do is now just substitute at the point where you have pi, put 180. So for example, 3 pi over 2, we can just substitute where there's pi, and then we can put 180. So that is going to be 90 by 3, which will give you 270. So that's how you convert between radians and also degrees. Okay, so I've got some more videos that you can watch under trigonometry, under sketching, double angles, solving trigonometric equations, identities, and also solutions to the tutorial sheet for UNZA students as well. You can have access to that if you register. So in the description there's a link to the platform that will allow you to register. So on that platform you'll be able to access all these videos and many other topics like binomial expansions, calculus, and matrices. Okay, of course including all the topics that you did in your first semester. So anyway, thank you very much for watching and have a lovely day. Okay, so let's break down the concept of reference angles. So what exactly is a reference angle? So of course we've got our 4 quadrants here. Let's take note. We've got from 0 to 90, that's the first quadrant, and then 90 to 180, and then of course 270, and then of course you get 360 there. Of course the radians I'm sure you know as well. So that is 0 radians, then that is like pi over 2. For 90, that is pi. This is 3 pi over 2. And then for 360, it's 2 pi. Okay. So what are reference angles? So the short answer is reference angles will be angles between 0 and 90. Or 0 and pi over 2 in radians. In other terms, I like putting it this way. A reference angle are angles that you get on your calculator. So if you try to punch sine inverse or cosine inverse of anything on the calculator, the angles that are going to give you are always going to be between 0 and 90. So these are reference angles. For example, you can take a case where you have a very simplest example you can have is if you have sine x being equal to 0.5. Now, if you want to find the value of x, you know that you're going to you'd have to say sine inverse of what? 0.5, right? So sine inverse of 0.5 will require you now to punch on the calculator. So if you punch on the calculator, it's going to give you 30. Okay, I'm using special triangles, which I believe you're already introduced to. So now, you understand, if you've studied trigonometry before, to say you don't only have a single solution to such a question. Okay, so when you say sine x is equal to 0.5, your first solution is x is equal to 30 degrees. So how do you find the other solution? So that's where now the aspect of reference angles comes in. So reference angles are going to be the angles in the first quadrant. They are the ones that helps us to find angles in other quadrants. Okay. Now it's also very important that you take note of the signs. So this is where we've got things like in the first quadrant, we've got all students take calculus, for example. So you have all these three, sine, cosine, tangent, being positive in the first quadrant. In the second quadrant, only sine is positive. In the third, only tan is positive. You understand why I'm telling you this later. So let's try to get a bit deeper. Okay, so I'll go back to the first question that I gave you, where we are considering sine of x being equal to 0.5. So the first possible solution is x is equal to 30 degrees after punching sine inverse of 0.5 or half on the calculator. Now, how do we find our solution? So this is now where the sign becomes very important. If you look at what we have, it is a positive 0.5. So we're trying to focus or look at the quadrant where sine is expected to be positive. And from what I've written there, we can clearly see that it's what? In the second quadrant. So how do we find an angle in the second quadrant? So we find an angle in the second quadrant by using the reference angle. Okay? Now, in the second quadrant, we need to subtract from 180. So it's always going to be 180 minus the reference angle. So I'll use alpha for that. So if you've got an angle, you just subtract the reference angle, you get the solution. For the third quadrant, since it comes after 180, you are going to add the reference angle to 180. For the fourth quadrant, you would have to subtract from 360. Now, I know already some of you are already asking, why are we not using 90 and 270? So, for your information, a simple thing I can help you with, or a tip to help you remember, always deal with the x-axis when it comes to determining angles in different quadrants. So if it is before 180, for example, you subtract the reference angle. If it is after, you add. 360, of course, you need to subtract. Okay, so that is for the first case. So if we are trying to find the other possible solution where we expect to have a positive 0.5, we know that sine is expected to be positive in the second quadrant. So therefore, we need to subtract from 180. So 180 minus 30 gives us 150. So that's the use of the reference angle in one case. Okay. Now, what happens in a case where we change the sign there? What if we had negative 0.5? What happens? So all the same, for us to find the reference angle, we need to ignore the sign. So obviously in this case, our reference angle is going to be 30 again, where we've ignored the sign. Now in this case, you notice that 30 is not going to be part of the solution set. Why? Because it's going to give us a positive result. So we are only using it as a reference angle to help us find the other possible solutions. The other solutions. So this is a case where the reference angle is not a solution. Okay? Because of a sign. So therefore, where do we expect sign to be negative? So obviously we know it's going to be negative in the third and the fourth. Because in the first, they are all positive. In the second, sign is positive. So it's going to be negative in the other two quadrants. So for the third, which comes after 180, we'd have to add the 30 to 180, which gives us 210 degrees. In the fourth quadrant, subtract from 360 gives us 330. So this is where you can now grab your calculator and try it out if you have it with you. So sine 210, sine 330, they are all going to give you negative 0.5. Okay, so for your practice now, I think I can now remove this diagram and then we see what you're going to do. Now let's consider a case where we have cosine, and let's say we had cosine of x being equal to root of 3 over 2. So find all the possible solutions, and then I also want you to look at the case where it is negative. Okay, so start with a case where it is equal to the positive part. So this is very important because you'd have to use your special triangles. So I'll just try to show you how again, in case you're not conversant. So this is a 30-60 triangle, expect to have the root of 3 and all that. Okay, so you can use the link in the description. There's a link about the video dealing with the special triangles that are very important. So let's say that we have 30, that we have 60. So we know sine 30 is equal to 1 over 2, right? So I can use that, opposite, and then of course we are going to have root of 3. So cosine x is equal to 3 over 2. One thing that helps me remember this faster is I know that cos 60 is equal to sine 30, which is equal to half, right? So therefore, the one who gives us root of 3 over 2 is cosine 30. So cosine 30, you can even try it out. If you say cosine 30, it's going to be, you know, so Katoa tells us it's adjacent over hypotenuse. So what is adjacent is this, and then the hypotenuse along your side is 2. So it's cosine of 30, precisely. So the first possible solution there remains 30. How do you find the other possible solutions? Where do we expect cosine to be positive? So remember, all students take calculus. Okay, very important. So where would you expect to find it? So cosine is positive in the fourth quadrant. So in the fourth quadrant, I said you subtract from what? From 360. So 360 minus 30, 330. So grab your calculator and try it out. It's going to give you root 3 over 2, a positive result. Okay. In a case where it is negative, I said the reference angle is not part of a solution set, so we'll just use it. So alpha is equal to 30. Where do we expect cosine to be negative? It's in the second and in the third. So for the second quadrant, we use 30 again. If we subtract from 180, we'll get 150. If we add to 180, it gives us 210. So if you try to punch that, they're going to give you negative root 3 over 2. So that is very, very important, and reference angles. Now, apart from all this, how else do we use the reference angles? Let me give you another scenario now where they are very, very useful and very, very important. This is a case where now we have not... Okay, let me just draw it. So this is a case where we can give you something like... it's just a random question. Let's say, what's tan 210, for example? You can't know. What is cosine? Maybe 240. Okay. What is sine 120? So all these, if you look at them, it becomes as though it looks complicated, but reference angles are there to help us. So if you look at 210, where do you expect 210? So I know that 210 comes after 180. So my 180 is there, so 210 comes after. Now, what is the difference between 180 and the 210 that we have? So if you subtract them, you realize that it's only 30 degrees, added to 180. So that has given you the reference angle. So the reference angle is 30. So you can now ask yourself, okay, so if I'm trying to find tan 210, it is going to be equivalent to what? Tan 30. Now we need to be careful with the sign. Which quadrant are we in? All. So all students take calculus. So we know that the tangent is, we know that tan is actually positive in the third quadrant. So the answer is going to be positive as it is. Okay? So positive tan 30. So now what is tan 30? So tan 30, we know sine 30 is equal to half. We know cosine 30 is equal to 3 over 2. So we can actually divide the two because we know from identity to say tan is equal to sine over cosine, right? So it's half divided by root 3 over 2, which is as good as multiplying by the reciprocal, which is 2. So the answer is 1 over root 3, even if you use your special triangle. Okay. So that's how you can use reference angles again. How about cos 240? Where is cos 240? So 240 also comes in the same quadrant. So subtract 240 by 180. That's a difference of about 60 degrees. So that is a reference angle again. Now this is a case where you now ask yourself again, so which one are we dealing with? We're dealing with cosine. Is cosine positive in the third quadrant? No. So cosine 240 is negative. So cosine is expected to be negative in that quadrant. So it will be negative cosine of 60 degrees as a reference angle. Which you know, of course, is equal to negative 1 over 2. Right? So I'm just trying to give you possible ways that you need to look at these questions. Okay. Now I can now conclude by showing you how you can actually approach the same concepts when you're dealing with radians instead of degrees. So the concept is one and the same. So let's say we have, you know that there is 0, that there is like pi over 2, pi over 2. There you have got pi, here you've got 3 pi over 2, and then there you have again 2 pi. Okay. So what happens? So whatever you're going to have, let's say you have sine of x being equal to 1 over 2. So you understand that there, the value of x is going to be what? In radians, 30 is what? It's pi over 6, right? So that is the value of 30 in radians. So in such a case, if you're trying to find the other possible solution, you need to ask yourself, just as we did with degrees, where do you expect sine to be positive? It's in the second quadrant, right? So the second quadrant is having pi, so we need to subtract from pi. So you can deal with fractions now there. How do we subtract fractions? So you've got like, you can multiply 6 times the pi there. The common denominator is 6, so 6 pi minus pi, which gives us 5 pi over 6, which actually, if you convert, should be able to give you 150. Okay, because the easier conversion that you can make between radians and degrees is where there's pi, you can always put a 180. That's the simplest way you can actually get to convert. So we're looking at reference angles dealing with radians. So it's the same concept. If you're not so conversant with radians, you can still be converting. You deal with it in terms of degrees, and then you basically get to convert. Okay, so we'll review Pythagoras theorem, very useful under the topic of trigonometry. So what exactly is this? So whenever you have a right angled triangle, I believe you know what a right angled triangle is. So where there's a right angle is a 90 degrees Okay, so of course we understand the triangle matches up to 180. So whenever you have such a right angle, where the right angle faces, the opposite side is the hypotenuse. So the hypotenuse is the longest side in a triangle, in a right angle triangle. Okay, so depending on the angle that you're looking at, if I'm looking at this angle to be theta, its opposite side is called the opposite. Its opposite, and then adjacent. Of course, if I also decide to look at that as my alpha, its opposite side is also going to be called its opposite, and then that side is adjacent to the angle. Of course, many people used to think or think actually that opposite and adjacent are fixed. It depends on the angle that you are looking at. Okay, so all the same, so adjacent and opposite don't matter. They depend on the angle that you're looking at, but the hypotenuse is always the same. So if we take the two adjacent sides to be A and B respectively, and then our hypotenuse to be, let's say, a C, the argument behind Pythagoras theorem is that the square of the longest side, which is the hypotenuse, is equal to the summation of the squares of the two adjacent sides. Just like that. That is the argument that is made. So what does that tell us? So it tells us in a case where you have 2 and 3. So for you to find the missing side, you understand that your longest side in this case is 3 squared equal to 2 squared plus the missing side. That's what Pythagoras theorem tells us. So you'd have a 9 minus 4 equal to x squared. 9 minus 4 is a 5. So until you get to find your answer as root of 5. That is the argument that was made by Pythagoras theorem. This is going to be very useful for as we proceed. Okay, so that's what Pythagoras theorem tells us. So in this video, I just want us to understand that tan theta is basically equivalent to sin theta over cosine of theta. Okay, very important for us to understand that very aspect. So some of the few things we'd have to look at to prove even that. We understand that whenever you're talking about sin theta from the first video, I told you to say sin theta is equal to 1 over 2. Cos theta is root 3 over 2. So if this is the case, we expect that tan theta will just be you dividing 1 over 2 divided by root 3 over 2. Now division requires to change to multiplication by multiplying by the reciprocal. So it will be multiplied by 2 root 3. So this would go away, and then the answer becomes 1 over root 3. That's a very important identity, and it's basically true. If you punch on a calculator times 30 separately, and then you also just divide 1 divided by that, you get the same answer. Okay, so even just identities for themselves show that, okay, from that special triangle, just in case you've forgotten, students. So this is 90. So I said if this is your 30, you can use sin theta to remember, because you understand SOHCAHTOA tells you so means opposite over hypotenuse. So it means your opposite is a 1, which is a 1. Your hypotenuse is a 2. So if you use Pythagoras theorem, which we've also talked about, you find that the missing side is root of 3. So if you try to find tan directly, tan, which is TOA, when you look at SOHCAHTOA, it is tan opposite over hypotenuse. Opposite is 1, and then over adjacent, sorry. So it is actually the same, 1 over root of 3. Let's basically get to understand what cosec, sec, cot are. So cos stands for cosecant. Cosecant. This is secant, and that's cotangent. Okay. So the way I usually help myself remember this is, it says cos, but I'll do the opposite, is sine. And then the one that starts with sec, which is related to sine, is basically cosine. Then cot, of course, is tan. Now, not necessarily that they are the same, Now it's a reciprocal of what I've been writing. So cosecant is the same as 1 over sine theta. That's cosec. Secant is 1 over cosine theta, and then cotangent is 1 over tan theta. Now we understand that from the previous video to say tan theta is actually equivalent to sine theta divided by cosine theta. Okay, we do understand that. So if that is the case, if you say it is 1 over sine theta, we're just substituting now where there was tan there. So the reciprocal of that will give us cosine theta over sine theta. So cosine of theta over sine theta is also cotangent, same meaning. Okay, so that was very, very important for us to talk about in this video. At this point, we've looked at the introduction to trig ratios. We've looked at the triangle, Pythagoras theorem. So we'll use that basically to build our basic identities, very useful and essential. So here is our right angled triangle. So we've said there's a 90 degrees there. Of course, where it faces the opposite side is called the hypotenuse, which is the longest side. So take it to be our C, that to be our A, this to be our B, and then we'll let the angle inside there be equal to, let's say, theta as our angle. So let's basically get to build some identities here. So according to Pythagoras theorem, we already know that C squared is equal to the square of the other two adjacent sides, which is A squared and B squared. We understand that already. Okay, now let's try to divide both sides by C squared. So divide everything by C squared, which tells us essentially that we've not changed anything about the equation because we've done everything to both sides. So it will be 1 on the left. So we'll now take the square. So A squared over C squared is just the same as A over C, and then just squared. B over C as well, we'll just pull out the square. Okay, now we can basically look at this angle theta that we are looking at. So if we say sine theta, what does SOHCAHTOA tell us? SOHCAHTOA tells us it's the opposite, which in this case is A, over the hypotenuse, which is a C. Of course, I did explain in the first video. You understand what SOHCAHTOA stands for. When you go to cosine theta, the adjacent is the adjacent over the hypotenuse, A over C. Okay? And then if you go to, is it tan? What are you going to observe of tan? So tan is basically going to be, so wait a minute, what did I do? So on the cosine part, the adjacent side of this angle theta is actually B, not A. So it will be B over C. In fact, that's enough. So substitute the letters with the angles. So A over C is sine theta. So it will be sine squared theta, plus, and then B over C is cosine. So it's cosine squared theta. Okay. So that is our basic identity. Very, very important. Okay. So we've derived our basic identity. So in the next video, we'll come up with other identities built from this very one. From the previous video, we've basically derived this identity. So now basically get to come up with more identities using this very one. Okay? Remember we talked about the cosec, the sec, and the cot. I said the cosec secant is basically equal to 1 over sine theta. And then I said cotangent is 1 over tan, or which is essentially cos over sine. And then of course we did also talk about sec, which is secant, which is 1 over cosine theta. So we can divide the entire equation by sine squared theta. So some of these things, if you just know at first equation to say that sine squared theta plus cosine squared theta is equal to 1, then you're able to derive the other identities from there. So what do we know? So we know if you divide something by itself, it will give you a 1. So we have a 1 there. Now cos over sine, I said 1 over tan is the same as cos over sine. So we did talk about the tan identity. So cotangent is also equal to cosine over sine theta. So that is cotangent. Now it is squared, so it will be cot squared theta. Then 1 over sine, we said it's cosecant. So since it is squared, it's also going to be cosecant squared theta. So that's another identity that is going to be very useful as we proceed. Okay, take note of it. So our second identity has also been derived. Now the third one is also going to come from the first one. Now what is going to happen here is we divide now by cosine squared theta. So as you might guess, cos squared theta, cos squared theta, cos squared theta. So what do we have now? So sine over cosine, I did tell you to say sine divided by cosine is tan. Now since it's squared, it's tan squared theta. And then cos divided by cos squared itself is 1. 1 over cosine, we said it is secant. So it is secant squared theta because of the square. So this is our third identity we've come up with so far. Okay? So with this very understanding, we are now ready to proceed and now look at proving some identities using the basics of the identities we've come up with so far. We'll progress and use the basic identities we've derived now to basically get to verify the trig identities. So I've got 3 that I want us to basically get to verify. So a few things that I would advise you when you're verifying identities is, first of all, prefer to choose from a complicated side, okay, to reduce it to the simplified part. So obviously if you look at this one, you're clearly able to see that the left hand side is more complicated, right? So select the left hand side, of course we understand is identically equal to cos x sec of x. And then the next step is usually to convert whatever is complicated to the cosine, the sine, and the tan. So in this case, we understand that we would have to convert sec, right? So that becomes identically equal to cosine of x. Now sec is what? Sec, we said, is 1 over cosine of x, if you remember from our previous video. So in the next step now, you can clearly see you have cosine of x multiplying by 1, which will just be cosine of x, and then on the bottom you also have cosine of x, which is basically just equal to a 1. Now at that point, left hand side now becomes identically equal to the right hand side. Okay, hence verified or proven, depending on how the question has been phrased. We're on the bit more complicated one. So we have sin x squared x over tan squared x. So I said pick a side that looks more complicated. In this case, the left hand side looks more complicated, so we equally start with that. So left hand side is basically equal to sine squared of x. So I can put it in another way. So that is the same as dividing by tan squared x. Okay. And then the next point, so we have sine squared of x divided by, so tan squared is what? We said tan is the same as sine over cosine. So since it is squared, it will be sine squared x over cos squared x. Now we understand that we can change our division to multiplication, right? By multiplying by the reciprocal. So say multiply by, it will now be cosine squared of x, and then sine squared will be on the bottom. So at this point, what we have, what can we see? So you can see after multiplying these we divide, and what is remaining is now what? cosine squared of x, right? So I believe you now understand what cosine squared of x is. So if you go back to our basic identity that we started with, we said the addition of sine squared x plus cosine squared x is basically equal to a 1. So you understand, if you make cosine squared of x subject, the sine squared goes the other side, it becomes a negative, right? So on our next step, due to lack of enough space, I'll just say the cosine squared of x we've ended up with is the same as we can see from the identity that I'm trying to write, that it is 1 minus sine squared of x. So we can now see that the left hand side now becomes identically equal to the right hand side, hence verified. Okay, so this identity is very useful, very useful. Don't forget this identity. Of course, everything is important. Tan, remember, it is sine over cosine. Cotangent, sec, everything you have to know. Cosecant and cot, cotangent. Okay, so if you look at this identity, I'm going to use two ways so you can feel free to just pause the video and just try it out to see if you've gotten what we've done so far. So obviously, if you look at the side which looks more complicated to me, I'm able to identify the left hand side again. 2 minus sec squared of x. So the first way I can handle this is, what do I know? I know that if we are saying sec squared x, what are we trying to say? So sec squared x, I basically understand it is 1 over what? Sec is 1 over cosine. Now it is squared because sec squared x. So 1 over cos squared x, that's our left hand side. We can still go a bit further. How can we handle that? What if we try to subtract? Common denominator becomes cos squared x. The other side, if you divide 1 into that, it will just be cos squared x, which will now be 2 cos squared x. And then if you divide it, just be a 1 like that. Are we getting any closer? So we don't seem to be getting any closer, but I feel there's a way we can handle this. How? I personally feel, understand, for us to have tan squared x being a result there, that would mean we have to get to a part where we have sine squared of x dividing by cos squared x, right? So we can only do that if we basically change what we have on top. Now if we go back to that identity, we understand that we have sine squared x plus cosine squared x being equal to 1. So if we have cosine squared of x, what can we put there? Now this is why I have to be smart now. If you make it the subject, again it will be 1 minus sine squared x, right? So we can say where there is cosine squared x, or substitute, it's the same as 1 minus sine squared of x minus 1 divided by cosine squared x. So I can remove these steps. Hopefully you wrote them down. Again, I'll proceed. So if we multiply by the 2, we have 2 minus 2 sine squared of x minus 1 divided by cosine squared of x. So we can see what we have like terms, right? Which 2 minus 1 is just 1, and then you still remain with 2 sine squared of x. So, and then of course our common denominator is still cos squared of x. So cos squared of x. Are we able to think of any way of simplifying that from that point? Okay, well, we'll try. So since we have a common denominator, we can try to divide by it directly. So we'll divide. So cos squared x, cos squared x. At that point, 1 over cos, we understand it is secant, so it will be sec squared of x, and then minus sine divided by cosine is the same as what? Tan, so it will be 2 tan squared of x. Okay, looks interesting. Are we any closer? It seems we're a bit closer. We just want to remain with now tan squared x, and then the 2 is supposed to go somehow. So if I think of an identity that combines these, I can take myself back to, let me take myself back to the basic identity where we said sine squared of x plus cos squared of x is equal to a 1. So the only way we can get to see sec is by dividing by, we understand secant is what? Secant is the same as 1 over cos. So we'd have to divide by cos squared x, the entire equation. So if we do that, cos squared x, cos squared x, cos squared x. So here we have tan squared x. I'm just trying to bring this identity in case you've not gotten used to it already. And then that is equal to sec squared of x. Any closer? Of course we are. So I can clearly see that sec squared x is equal to 1 plus tan squared x. I just wanted to show you that. So now we can prove now where the sec squared of x, we substitute tan squared of x, okay, plus a 1, and then minus 2 tan squared of x. Are we any closer? This is now going to give us like terms. This is like 1 tan squared x and then minus 2, so it will just be a 1 and then minus just tan squared of x. So at this point we can now see that the left hand side is basically equal to the right hand side, hence verified. And of course I can now try to show you the other way, that is if it's going to work. The left hand side is basically equal to 2 minus sec squared x. Now we've seen from the identity to say sec squared of x is the same as 1 plus tan squared x. So at this point we can have 2 minus 1 minus tan squared x, which is now proving this same identity in just 2 steps. Yeah, so that's our final answer. The left hand side now becomes the right hand side, unlike the other one. Anyway, the other one was just trying to teach us a lot of things about identities and different ways how we can handle it. So there's no wrong way of handling identities. What matters is you're able to get to what you've been given on the other side. So that's it for this video. So we'll get to solve just a few. Okay. So if you're actually enjoying this video, you can actually have access to the full trigonometric solutions that will allow you to understand the topic fully. So the question 1 is there, the question 2 is there, the question 3 there, the question 4. Identities are also there. As you can see, question 6 and 7 are based on identities. Double angles are also there. Okay. So you'll be able to understand the half angle principles as well, looking at question 4. And then as we go to question 8, you'll also be able to understand how to go about it, how to solve trigonometric equations. Question 9 is also there, how to answer more equations. Question 10, dealing with sketching. Question 11, dealing with sketching. Question 12, dealing with sketching. Question 13, sketching as well. And then you also understand how to determine or evaluate these trigonometric kind of expressions, looking at question 14, 15, and also 16 as well. So you can have access to all these solutions by just registering. So you can visit our site, the link is in the description. From there you can also learn the topic from scratch, each basic concept step by step, and also access the solutions to this entire tutorial sheet. Equations using the identities that we've learned about already. So I've got 2 questions to help us understand the basic idea behind the calculations. So 2 tan squared of x is equal to sec squared of x. How can we basically get to find our solutions? So of course we'll solve our solutions between negative pi to positive pi. Okay, in this kind of a video we'll restrict ourselves to that. Okay, so if you look at this equation, it looks a bit interesting. Not so, it does look interesting. Now tan squared of x, and then you've got sec squared of x. how can you handle this question? So you understand it's better to deal with tan than sec, because at least you know of the tan identities we talked about later or earlier on in the series of trigonometry. So if you go back to identities, where we are building from the addition of sine squared x plus cos squared of x is equal to 1, how do you derive sec squared of x? So we said you get to divide by cos squared of x into that identity. So of course we saw that. I'm now hoping you now remember that sec squared of x is equal to 1 plus tan squared of x. Okay, so we can now correct like terms. So we have 2 tan squared of x minus tan squared of x minus 1 is equal to 0. Do we have any like terms? We do. 2 minus 1 is just tan. So I have tan squared of x. I can choose to say minus 1 as it is equal to 0. Now we can square the 1 so that we have a difference of 2 squares. So that would mean we have now tan x minus 1 and then tan of x also plus a 1 equal to 0. So we can have now two equations there. So the first one says tan of x is equal to 1. The other one says tan of x is equal to negative 1. So I'm just getting them and of course equating them to 0. So these are the two equations that we have. Now if you go back to identities, do you remember any identity that had given us tan basically being equal to a 1? Any identity that you're able to remember in that form? Of course, I can take you back to this triangle if you do remember it. Tan 45. So 45, 45. Okay. So we said 1, 1, and then we said yeah, it was root of 2. So how do you find tan 45? So you basically get to find tan 45 as, so Katoa tells us for tan it is the opposite over the adjacent. So the opposite is the 1, the adjacent is also equal to 1. Remember where the 90 degrees points as your hypotenuse. So in this case it tells us tan 45 is basically equal to what? Is basically equal to 1 over 1, which is just like a 1. So you can see that one of the first possible solutions of our x is 45 degrees. 45 degrees. Now can you convert to radians? So 45 degrees is the same as pi over 180 degrees. If you so multiply by pi over 1 over 80 if you want to convert to radians. So how many times can 45 go into 180? We know in 90 it's twice, so in 180 it's going to be 4 times. So we have the answer as pi over 4. So pi over 4 is one of the possible solutions to satisfy that equation, pi over 4. Now, how else can you interpret that? So now the other way that you can think about that to find the other possible solutions, we did also talk about it in the introduction to trigonometry, finding the angles in the other quadrants. So we said whatever you basically get is from the first quadrant. Now what matters is how you get to find the other quadrant. So this is for all, and then all students take calculus. So where do we see our tan to be positive? So it's obviously in the third quadrant where we are seeing tan. So this is of course 180. In radians it's just pi. That is pi over 2. Okay, that is 2 pi. Of course this should be 3 pi over 2 if I'm not mistaken. Okay, so with that understanding, how do you basically get to find an angle in the third quadrant? In the third quadrant we said you add to pi, right? That's what we said. So Another possible solution to the tan x is equal to 1 is pi over 4 plus pi. Okay, so of course you understand the common denominator is a 4, so it will be, if you basically get to add there with a common denominator of the 4, you have 5 pi over 4 as also one of the possible solutions. Okay, the fastest way of basically getting to add that is multiplying by 4 multiplied with the pi. It will be 4 pi plus the pi that is there, it gives you 5 pi over 4. So you've got two solutions already. Now the good part about trigonometry is if you have the same value being negative, this is the same value. We've seen that tan 45, which is tan pi over 4 in radians, gives us 1. So if you change -1, all you just have to do is you use this pi over 4 as you learned under difference angles as your reference angle. Now try to identify the quadrants where you expect that where you expect tan to be negative. So obviously it's in the second quadrant where we have sine, and also in the fourth. So how do you find an angle in the second quadrant? So you find an angle in the second quadrant by subtracting from pi. So we use our reference angle and subtract from pi. So our reference angle was basically pi over 4 because it's the one that gives us a 1. Now we can use the same one to find the parts where it is negative, because we're trying to find where it is negative, of course. So we'll say now pi minus pi over 4 as one of the possible solutions. And then the other one, of course, how do you find an angle in the fourth quadrant? Find an angle in the fourth quadrant by subtracting from 2 pi, which is of course equal to 360. So again we'll subtract from 2 pi. So 2 pi again minus pi over 4. So you know how to basically subtract fractions and whatnot. So here the solutions will be after subtracting from pi, it's going to be 3 pi over 4. And then after subtracting from 2 pi, it's going to be 7 pi over 4. So these are the 4 possible solutions to the equation that we basically have. And this is how you're supposed to handle this question. Okay, so with that idea, let's now try to attempt this one. So you can pause the video and basically try this one out. Okay, so we saw that sine squared of x plus cos squared of x is equal to 1. So in a case where you want to basically get to, you understand that one has got no identity, so this one has an identity, we can use it to simplify this. We know sine squared of x is just the same as 1 minus the cos squared of x. That is the same identity we're talking about of addition, and then the cos squared of x goes the other side of the equation. This is what is going to stand. And then of course as you multiply by 2, you have now 2 cos squared of x, and then plus cos x. We can bring the one this side equal to 0. Collecting like terms, the one with a square will now be 2 cos squared of x, remaining with plus cos x on the middle. 2 minus 1 is just the 1 equal to 0. So at this point, what can you see? You can now see that you are now remaining with a quadratic function. Okay, a quadratic function. So you are also capable of factorizing it. So this is squared, that is just b, and then that is c. So our product is obviously going to be -2 times 1, which is just a -2. The sum is what is on the middle, which is a 1. Which two numbers can you multiply to give you a -2? You add them, they give you a 1. So it's obviously 2 and -1. 2 times -1 is -2. 2 plus -1 is just a +1. So what are the factors? So we have -2 cos x, and then we can say plus 2. Again, the other part we can say -2 cos x, and then -1. The other way of handling that is, of course, you basically just get to substitute on the middle. You have 2 cos x, and then you have minus cos of x. So it's still 1 in the same way. So of course equal to 0. So now you have two equations as well. So we have negative 2 cos of x. So if this goes the other side, it will become minus 2. You can divide both sides by negative 2. You end up having cos x is equal to just a positive 1. And then the other side, you have negative cosine of x. It goes the other side, it becomes positive 1. So we have now cos of x being equal to, so after dividing by a minus 2, you have now negative 1 over 2. Okay, so how basically can we answer this question? So if you look at cosine of x being equal to a 1, you now think of which angle, if you plug in where there's x, will give you a 1 for the cosine function. So in case you've forgotten the cosine function from our introductory video, it was something that came out this way. It was starting actually from the top part there like this. So we saw that cos 0 and also 2 pi, which is 360, are the ones that were giving us a 1. Okay, so what are the two possible solutions? That is 0 and then 2 pi. Now for the part where it is negative 1 over 2, you'd first of all have to think of the one that can give you a positive 1 over 2. So again, the same graph. That's the way it is. That's our graph. So that one was giving us cos 1 over 2. So if you go back to the 30 and the 60, the triangles actually are the ones that are useful in terms of the half. So you remember that it was basically 60. Cos 60 degrees was basically the one that was giving us a positive 1 over 2. Now 60, if you take it to radians by multiplying by pi over 180 degrees, you have 60 there, it's 1, you have 60 there, it's 3. So you have pi over 3 as your 60, right? Now pi over 3 is not a solution because this will give us a positive 1 over 2 if you take cos of that. So I want to find the quadrants where cos is negative. So all students take coffee or calculus. So it's in the second and the third quadrant, right? Second and third, sine, tan are positive. So cosine is negative in those two quadrants. So one way will be subtracting from pi in the second and then of course adding to pi. So that's the way you're going to find the other two solutions. So if you subtract from pi, you have 2 pi over 3. If you get to add to pi, you have 4 pi over 3. So ultimately, these are the possible solutions you can have: 0, 2 pi, 2 pi over 3, 4 pi over 3. That will be able to satisfy that equation there. Okay. And then finally, these are the practice questions that you can attempt to test your understanding of whatever we've talked about. So keep these questions for the sake of the classes that are going to be conducted over the weekends. You can ask your tutors for more information. Okay, so in this video we're just going to go over the negative angle identities. Okay, before we even get to look at the identity itself. There's an identity we're supposed to answer, but first of all we have to understand these negative angle identities. So I'll start with sine negative of x. So sine of negative of x will be as simple as, it's the same as negative sine of x. Then if I talk about cosine of negative x, so cosine is the only one that changes, so it becomes the same as positive cosine of x. Okay, so tan remains as sine, so tan of negative x is just the same as what? So it will be a minus tan of x. So you've observed that the signs of x are changing. Okay, now the only sign that is the opposite is for cosine. So equally, as I get to talk about the aspect of the cosec, the secant, so we understand which one is associated with cosine. The one that is associated with cosine is secant. So equally, the same things will apply for cosecant, which is associated with sine. it will be negative, it will maintain. The secant will become positive, and then the cotangent will get the negative from its x. So only two of these are different. Cosine, which is associated with secant, because secant is 1 over cosine. So those are the only ones that if you remove the negative from the x inside, it becomes a positive on the forward part. Okay, that is cosine and secant. These are the negative trig identities you'd have to know and work with. Now talk about this identity or prove using the identities we've come up with under the negative angle identities. So cosine of negative x we've basically seen. So the left hand side is of course more complicated. So the cosine of negative x is obviously going to be positive, as we've seen. It will be positive cosine of x. And then for the sine, it will become negative now. 1 minus sine of x. That's what we've seen from the negative angle identities. Now at this point, checking that actually the top part, the other side, the right hand side, is only a single line. So we'd better want to do away with the denominator. So the best way we can do that is by multiplying by the aspect of the conjugate. So we'll multiply by 1 plus sine of x. Again, we'll say multiply plus. So this is just the same as we are multiplying by a 1, because if you divide that, it will give you a 1. So we're not changing the equation, but we're just trying to simplify it. So if you multiply, you have cosine of x multiplied by 1, since it's in the brackets. And then you have cosine of x again. Maybe for the sake of simplification, let me first of all read it in the brackets. 1 plus sine of x. And then in the denominator part, 1 times 1 is just a 1. So understand that with what we have, if you multiply the middle part, it's basically going to go away. So in short, what we just have is like a difference of 2 squares. So it will just be 1 minus sine squared of x. Okay. So now at this point, we wouldn't want to expand it again, because if we do, we are going to reverse whatever we've done. So what we're going to do is, we understand that the different form of 1 minus sine squared of x is the same as cos squared of x. And then the numerator will maintain. So due to lack of enough space, I'll proceed on the top part. So we'll have cosine of x 1 plus sine of x. And then 1 minus sine squared of x is of course equal to cos squared of x. Are we any closer? Yes, we are getting closer and closer. So you understand that that can divide into 1, and then on the denominator part there remain cos x. So where are we getting now? So we now have 1 plus sine of x over cos of x. So the common denominator is cos, so we'll say 1 over cos, and then we'll say sine also over cos separately. So now 1 over cos is something that we know as an identity, right? 1 over cos is sec of x, and then sine divided by cosine is tan x. So at this point, this is what the left hand side has become. So you can now make a conclusion, a statement. So the left hand side is identically equal to the right hand side, hence verified or proven, depending on how the question was phrased. Alright, so we're going to proceed and talk about the addition formula. So we've got 6 that you'd have to understand. So I'll introduce you to them, and then in the next video we'll proceed and look at some questions we can answer using the addition formula. Okay, so the first one deals with sine. So sine, so we'll assume now we are adding two things. Okay, when you have sine a plus b, what does it mean? Okay, or what does it simplify to? Okay, so this is what we're going to have. So sine tells us it's going to be basically equal to the sine of A, which is in the brackets, and then multiply by the cosine of B, and then the sign in between will be maintained according to sine. So it will be plus. Now on the other part, you'd have to exchange. So notice that we started with sine of A and then B, cosine of B. So this time around it will be cosine of A and then sine of B. This is something that is interesting about sine. Okay. And then of course, the other thing we'd have to look at now is an aspect of the negative sign. So the negative sign tells us, of course, you'd have to just guess. So if you say sine A minus B, it will be the same concept. So it will be sine of A, cosine of B. The sign in between will be different, but everything stands the same. So in short, there is a correspondence in terms of the signs when you're dealing with sine. Now let's look at the additional formula for cosine on the other hand. So for cosine, if you have A plus B, unlike what we saw under sine, for the cosine, what's basically going to happen is we'll apply cosine to both A and B. So it will be cos A. So as we expected for sine, it was going to be sine B. Now this time around, it will just be cos again B. And then the sign changes in between. Again, you apply sine to both A and B, sine A, sine B, respectively. This is the difference between the sine and the cosine additional formula. So if you consider a negative sign in between, you expect that the sign will be the opposite. So the easiest way of remembering this is, we've seen that for sine, basically sine is somehow, I call it fair. Yeah, I call it fair. Sine is fair. So sine will share, it will share with A, sine A, and then cause cosine to come and help with B, and then add, again they will exchange. That's the way sine. So sine is somehow fair. That's my language to help me remember. So obviously the same applies. Again, sine will get A, and then cosine will get B, and then subtract and gain exchange. Now for cosine, cosine is selfish. It will apply itself to both A and B, cos A, cos B, and then minus. That's when sine will also now get chances to do both A and B. And then the other thing is, for cosine, the sign in between basically gets to do what? Gets to change. So these are additional formulas that applies to sine and cosine. So now that we've dealt with sine and cosine additional formulas, we're going to proceed in this video by now looking at the tan. Okay, so what if we have now tan A plus B? Now the good part about our identities is we've already earlier talked about tan. So we said tan is the same as sine. So tan A plus B is the same as sine A plus B divided by cosine of A plus B. We understand that identity that we learned earlier in the series of trigonometry. Now at this point, what are we supposed to do? So we've now seen how we basically get to expand all this. So sine of A plus B, we said sine is fair, it will get A, and then cosine will get B, and then the sign will be maintained. So it will be sine. On that other side, we expect to now have cosine of A and then sine of B. That's what we expect to have. And then with our colleagues here now, cosine is selfish, so it will get both A and B first before giving the other one, and then the sign changes for cosine, so it will be now sine A, sine B. Okay, this is where we've got to now. So applying the very concept of knowing that tan is the same as sine over cosine, so we'll basically get to divide the entire equation we have. Both the numerator and the denominator will divide by cosine of A, cosine B, every part. to simplify it. So notice at the top part we have sine A cosine B plus cosine A sine B. Now we've said we are dividing by this part, the entire thing. So we're dividing by cosine of A cosine of B, cosine of A cosine of B. Then of course divided by, so our denominator we had cos A cos B minus sine A sine B. So we're dividing again. We're dividing by what? We've said we're dividing by cosine of A cosine of B, which of course if you divide it by itself there will give us a 1. Cosine of A cosine of B. So we are now trying to derive the tans. So if you observe there, of course that would divide to give us a 1. That's identical. That is also identical. Cosine A cosine A. What else is identical? This is identical to give us a 1. Is there anything else identical? So begin identifying. So if you check the remaining part for the first part, sine A divided by cosine of A, those are matching, they will give us tan A plus. This side, sine B divided by cosine of B will give us tan B over the denominator we have a 1 minus, can we try to observe something? So sine of A divided by cosine of A, that will give us tan A, and then sine B cosine B, that is also tan B. So this is basically the identity that deals with tan, as simple as it is. So you can know it. So it's just basically, it's as simple as if you have tan A plus B, distribute tan to A plus B as it is, and then divide by 1 minus the product. So obviously, essentially, if you have tan now, A minus B. So I will do the same. I believe it should be tan A and then minus tan B. And then denominator the sign will change again, the product tan A tan B. So that's basically how you basically get to handle this. This is simple and straightforward. So this is the tan identity when it comes to additional formula. Okay. So now in the next video, let's now look at questions how we can apply this additional formula. So we now have the 6. They are all 6 now. 2 in this video, 4 in the previous video. So let's proceed and see what we can have. So now apply the additional formula to answer this question, sine A plus B. And of course for the other question we would have to answer now is sine 75 degrees. How basically can we handle that? So we use the additional formula to answer these two questions. So I'll start with sine A plus B. So we earlier saw that sine A plus B, we said sine is fair. So it will be sine A, and then it will share with cosine, and then the sine is maintained, and then cosine will now get A, and then sine will now also get B. So it's just an exchange there. That's the way it is. So what basically do we need? We need sine A, which has already been given. Cosine B has already been given. So now we need cosine of A and sine of B. Okay. So we'll apply the concept of trig ratios to find the other angles. So I'll draw the right angle triangles. Okay. Then we can have another one. Don't mind my drawings, I'm just trying. So that is 90, that is 90 as well. So sine, according to Sokatoa, what does it stand for? So sine is opposite over hypotenuse. So opposite over hypotenuse. So taking this angle to be A, its opposite is the other side, which is going to be 3, and then the hypotenuse is a 5. Okay. Now k, which is cos, tells us cosine is equal to adjacent over hypotenuse. So taking this angle to be b, its adjacent is this down here, which is going to be 5, and then the hypotenuse is 13. I'm looking at that now, opposite over, sorry, it's now adjacent since it's k, so adjacent over hypotenuse. That's another triangle. So I've come up with two triangles using the given identities on top. So now this is 5. So we now understand that we're able to find the missing sides using the Pythagoras theorem, which we know of already. So we'll say let this be a. So 3 squared plus a squared should be equal to 5 squared. That is 9 plus a squared is equal to 25. So we have a squared is equal to 25 minus 9. 25 minus 9 is what? That is 16. So a is obviously going to be 4. So found the missing side there. It's 4. And then we can go to the other triangle as well. Pythagoras theorem tells us the square of the hypotenuse, which is of course the longest side. So 13 squared is what? 13 by 13. That is 9, 1. Yeah. No. 9, 3. 3, 1. 169. Okay. Just trying to be sure. So we have 169, which is the square of 13, is equal to the addition of 5 squared, which is 25, plus a missing side, we'll call it b squared. So we have 169 minus 25, that is 144. 144. So b squared, of course, we have plus or minus 12. 12 times 12, I believe, is 144, right? Yeah. So 12 is b. So we have 12 there. So we now have found all the missing sides. So in terms of identities, what was missing? We had cosine of a missing. So cosine of a, we use the triangle having a. So cosine of a is going to be cosine, according to Sokatoa, it tells us for cosine it's, if you look at cosine, it's adjacent over hypotenuse. So the adjacent of a is 4. The hypotenuse still remains 5. In the other triangle, we're trying to find sine b. So sine of b tells b, sine means opposite over hypotenuse. So opposite is 12, the hypotenuse is 13, 12 over 13. So found all the missing angles. I can clearly erase everything now. So we can now substitute in our formula there. So sine of a is what? Sine of a was really given to be 3 over 5. Cosine of b, 5 over 13. And then cosine of a, we found it to be 4 over 5. Sine b is 12 over 13. Okay, this is now simple mathematics. You're able to simplify from that stage, right? 5 can cancel out. You have 3 over 13. How do you simplify the other part? 4 by 12 is 48. 5 by 13. Am I able to simplify that? 5, 6. It's 65. Yeah, 65. And then, of course, you can add the fractions yourselves. So add that. So you'll be able to get your answer. So that's basically the key important thing, is being able to use what we're given, come up with a triangle, and of course the formula will help us to expand, which I believe we are now very much acquainted with. So for the sake of your practice, I would want you to now simplify cos a minus b as one of the other questions. Okay, now I also did promise to say I'm supposed to talk about how you can find sine 75, for example, without using a calculator. How do you simplify that? So it may be a little bit complicated directly, because 75 is not a special angle. But we know of a special angles. What special angles do you know of? I know of 30. I know of 60. In fact, 45 is also missing. 45 is also one of the special angles. Yeah, these are the special angles I know of. Of course, 90 is also one of the angles you're able to derive. So 40, 60, 45. These are the special angles we know. So are you able to express a given angle in terms of a summation of the special angles? So 75 is the addition of 45 and 30. Okay. So if we know that, then we are home and dry. So sine 45 degrees plus 30 degrees. Now from just looking at the additional formula, it tells us sine is fair. So it will be sine 45 cosine 30, and then the sine maintains. They now exchange cos 45 now sine 30. Okay, apologies, no enough space there. I'll now simplify on the next part. Sine 45, I'm not able to remember sine 45. So there's this triangle we did talk about in an earlier series of trigonometry from the first introductory video. You can go back to it if you've forgotten. Said 45, 45 is one of the special triangles. And then you said these sides are equal. So if you use Pythagoras to find this other side, it is root of 2. So if we're trying to find sine 45, sine 45 tells you. Now the good part about a 45-45 triangle is the adjacent and the opposite are basically one and the same for every view of 45. So therefore sine 45 is basically going to give us what? 1 over root of 2. Since Sokatua tells us sine opposite over adjacent, cosine, yeah, so 1 over 2. And then cos 30. Cos 30 takes us now to the other triangle. The 30 is the triangle. So of course for any information, from the 45 we need cos 45 later on as well. So cos 45 as well is 1 over root of 2. So cos 45 and sin 45 are the same. That's why tan 45 is equal to 1. So let me just draw the other triangle, 30, 60, in case you've forgotten it. So I gave you a tip on how you can remember that easily. I said sin 30 is 1 over 2. So do well to say sin 30 is 1 over 2. So the longest side is 2. Of course, if you try to use Pythagoras, the missing side will be root of 3. So cos 30, cos is adjacent over hypotenuse. What's adjacent of 30? It's root of 3. So I have root of 3, the hypotenuse is 2. Plus cosine 45, we've also said it's also 1 over root of 2. Sin 30 is the common identity, which is 1 over 2. The common special angle. Okay. So what do we have at this point? So I have root of 3, 2 root of 2, plus 1 over 2 root of 2. So 2 root of 2 is a common denominator. And then you have root of 3 plus 1. So this is basically how you can simplify that without using a calculator. So basically, it's just a matter of you being able to express 75 into the summation of its angles. Of course, now applying the additional formula to expand that to get to this point. So for on practice, try now out cos 45. So I'll just give you cos 75 degrees. And then what else can you try out? What if I give you, of course, the special angles of cos 45. What's so? Okay, let me do this. Try to simplify this. Okay, let me not complicate things. I'll just say sine 105 degrees. Yeah, that's fine for practice. And then the next video I'll proceed and look at now the double angle formula. Okay, so if you're actually enjoying this video, you can actually have access to the full trigonometric solutions that will allow you to understand the topic fully. So the question 1 is there, the question 2 is there, the question 3 there, the question 4. Identities are also there. As you can see, question 6 and 7 are based on identities. Double angles are also there. Okay, so you'll be able to understand the half angle principles as well, looking at question 4. And then as we go to question 8, you also be able to understand how to go about it, how to solve trigonometric equations. Question 9 is also there, how to answer more equations. Question 10, dealing with sketching. Question 11, dealing with sketching. Question 12, dealing with sketching. Question 13, sketching as well. And then you also understand how to determine or evaluate these trigonometric kind of expressions, looking at question 14, 15, and also 16 as well. So you can have access to all these solutions by just registering. So you can visit our site, the link is in the description. From there you can also learn the topic from scratch, each basic concept step by step, and also access the solutions to this entire tutorial sheet. Now that we've talked about the addition formula, it's going to be very easy for us to understand the double angle formula. Very simple. Okay, so what we proceed, want to proceed this way. So just a few things to understand is maybe just to remind you of what we've learned so far. So it said sine a plus b is the same as what? So I said sine is fair. So it will share with cosine. So sine a, and then it will share b with, and then again we'll say the sine is maintained, and then cosine will get the a, and then sine gets the b. Okay, so the double angle formula gets to come from all this. So if we say sine 2a, for example, we understand sine 2a is the same as sine a plus a, right? So sine a plus a, think of it in this way. So apply the same principle. So what will basically just come out is, at every point where we are now, of course, let's take it as it is. Sine is fair, sine a, it will share the other a with now cosine of b, and then of course cos a sine a. So since we have a's everywhere, so I can change the order there. Multiplication doesn't matter what you start, so it's the same as sine a cosine of a. So this and that are the same. So in short, you just have 2 sine a cosine b. Now this is the double angle formula. So 2 sine a cosine of b. Applying the same principle, if we go to now cosine of a plus b, we said cosine first of all wants to eat first of all before anyone eats. So it will eat both a and b, cos a cos b, and then it changes its sign, and then it will now share with sine a sine b. Now consider a case where you now plug in cosine of a plus a. So a plus a is, so it will be cos a, it will get both a's, cos a, and then it will also now give sine both a's. So notice that these are just repeated. That's repetition now. So cos a plus a is the same as cos 2a, which is double angle. I'm just applying the additional formula. So cos a multiplied by cos a is cos squared a. Sine a multiplied by sine a is sine squared a. That's cool. This is another double angle formula. And then finally one more. So we said tan a plus b. We said tan maintains the sign, so it will be tan a plus tan b. And then we said it was 1 minus the product of tan a tan b. What do you expect to have? So if you say tan a plus a, on top it will be tan a plus tan a, which is going to be 2 tan a, and then the denominator 1 minus, so it should be tan A, which will be tan squared of A. So this is now the double angle formula. So tan 2A is basically equal to that. So if you know the additional formula, just now plug in A plus AX plus X, one identical thing. It now gives us what we're now calling the double angle formula. Okay. So this is how you basically get to derive these. So now let's see in the next video how useful they are and how we get to apply them by trying to see how we can simplify sine 3 of x, and then also solving an equation using the same. We'll look at it. So now practicing the double angle formula, we'll look at two interesting questions. So the first one is basically getting to solve an equation. Let's say we've given you cos 2x is equal to sine of x. How basically can you simplify this? Now it becomes a bit cumbersome because if you look at that cosine of 2x, again it becomes an issue. Why? Because it's a double angle. So how do you simplify that? So we've already seen that cos 2x is the same as x plus x. So from the double angle formula, just in case you've forgotten it, think of it in this way. It's just x plus x. Okay, and then apply the additional formula. So we saw that it was giving us cos squared of x and then minus sine squared of x equal to sine what? Sine x. This at least looks a bit easier, but of course whenever we're trying to solve this, we just want it to be identical. So we have sine there and then we have sine there, so we can convert the cosine. Remember, now think of that identity now. Sine squared of x, cos squared of x is equal to 1. So if you want to make cos squared of x subject, this one goes the other side, it becomes 1 minus. So where there's cos squared of x, it's the same as 1 minus sine squared of x, so equal to sine x. So I'm just using identities now to simplify this equation. At this point, I can see we have now negative 2 sine squared of x. Let me write that better, sine squared of x. And then if sine x goes the other side, it becomes now negative sine x, and then plus the 1 equal to 0. So we've now come up with a quadratic formula. Okay, so I did teach you how to solve such equations earlier. So for a practice, you can now handle this question and get to see if you're able to handle it. So I was just trying to show you how basically you can use identities to simplify all that. Okay, so after you find it, so the expected solutions are pi over 6, 5 pi over 6, and then negative pi over 2. The other question that I'd want us to handle is now a case where they ask you to simplify sine 3x in the form of sine x. Take it to form of sine x. How can you handle that question now? So from addition, we've already noticed that sine 3x, we can simplify it as the addition between 2x plus x. So I'm trying to use a double angle because it's going to be easier. So even in the case where they give me sine 4x, I know I can put it as sine 2x plus 2x, since the double angle formula is something I'm very familiar with. Okay, so let's handle that. So sine of that is going to be, we'll distribute the sign, so it's the same as sine 2 of x and then cosine of x, and then the sign maintains. It will now be the cosine of 2x and then sine of x now. So how far are we now? So now we already know that sine 2x, we saw it from the double angle formula by expressing it as sine x plus x. What did it give us? It gave us, it was actually 2. So 2 sine x cosine of x, multiply now by cosine x, which is here.
So multiply by cosine of x, and then we have plus cos 2x, which was cos x plus x, gave us cos squared of x minus sine squared of x, multiplied by sine x, which is there. So are we any step closer to where we want to get? So if you do substitute there, if you multiply 2 sine x cos x, but so it will be now give us 2 sine x, so it will now be cos squared of x plus cos squared of x minus sine squared of x, so we'll maintain that as it is, derivatory. And then of course we understand we are multiplying by the sine of x that is out there. At this point, what can we do now? So we just want to see sine of x. So where there is cos squared of x, what I can do is I can now begin substituting. Now we understand that from that very basic identity, cos squared of x is the same as 1 minus sine squared of x. So I'll substitute. So we have 2 sine of x. Now where is cos squared of x, I'm now putting 1 minus sine squared of x. And then the other side, there's a sine x there. So in the brackets we have cos squared of x. I'll plug in now 1 minus, it is 1 minus sine squared of x. Now there's also minus sine squared of x there. Okay, so almost now there. What can we do next? I can open the brackets by multiplying with what is outside. So we have 2 sine x multiplied by that, it will be now be 2 sine cubed of x, and then if you multiply by sine of x, you have sine x. Again, if you multiply by sine squared of x, it will be sine the power 3x, and then it will be sine again. Why didn't I add these? So these are like terms. We can simplify that by just giving us a 2, so that if you simplify by giving you minus 2, it will just be minus 2 sine that cubed of x. Any like terms at this point? So if I check, I can see we have minus 4 sine cubed of x, and then 2 sine x plus sine x will give us 3 sine x. So we can write it as 3 sine x minus 4 sine cubed of x as our simplified form, or one way of expressing sine 3x in the form of sine x. So that's it for this video. I hope you now understand the importance of knowing the double angle formula. So I needed to mention that now what we've derived is another identity. Okay, so you can now know that sine 3x is the same as 3 sine of x minus 4 sine cubed of x. It's an identity that you can know as well. So for the sake of your practice, you can now try to undo cos 4 of x. Simplify that. Express it in the form of cos x. This is now how far we've moved. So we need to understand how we basically get to undo trig equations. So one thing that you'd have to know is we've already talked about them. I talked about them in the introduction to trigonometry and also under identities. So I'll just try to give you a recap of everything you'd have to know. So Beginning with the simplest one. Consider a case where they give you sine of x equal to 30 degrees, and then they ask you to find solutions. So solutions may be, they may specify, for example, solutions may be up to 360. For instance, x should be less than 360 degrees, and of course from 0. So how do you basically get to answer that question? So for your own information, in cases where calculators are allowed, but in most cases they're not allowed, x is going to be sine inverse of 30 degrees. In other terms, the question that is you're asking yourself is, what value of x, in fact, this is very, what have I done? So on the other side, it was supposed to be 1 over 2. Okay, so I'll not edit that. I just put that. So sine inverse of 1 over 2 is like, what angle can you put there to give you 1 over 2? So obviously we already know. So the answer is 30. Sine 30 gives you 1 over 2. I don't know why I put the 30 there. Okay. Now, if they tell you to say find all the possible solutions, for example, we're given such a domain 0 to 360, I did explain in the introductory video to trigonometry to say we need to basically understand the quadrants. Okay. So we understand that if you have an acute angle in the first quadrant, and then you want it to use you use it as a reference angle to find other solutions. Okay. So in this case, we understand that 1 over 2 is positive. So we'll ask ourselves where we expect sine to be positive. So it's only in the first and the second quadrants, because all students take calculus. So this is sine positive, tan positive, cosine positive. In the first quadrant, they're all positives. So for us to find the other solution, now I did also indicate that for you to find the solution in the second quadrant, you need to subtract from 180. So 30 from 180 to give us 150 degrees. So that's why if you get your calculator, punch sine 30, it's 0.5. Sine 150, it's also 0.5. Simple and straightforward, right? Okay. What if I try to change something about this? What if I add, maybe I can begin by adding a negative. What if I add a negative 1 over 2 instead of a positive 1 over 2? So in such a case, ignore the negative. We understand that the one that is able to give us a positive, again, we understand that we'll call it alpha, is 30 degrees again. 30 degrees is capable of giving us a positive 1 over 2. Now we're not interested in the negative, in the positive one. In this case, it's negative. So we'll just use that as the reference angle. So since we know it's positive in the first and the second quadrant, sine is going to be negative in the other two quadrants, third and fourth. So in the third quadrant, you find an angle by adding to 180, and then of course in the fourth by subtracting from 360. So 180 plus 30, so our x is equal to 210 degrees. From 360 to 330, and it's true, if you get your calculator, sine 210 is negative 0.5, 330 it's also negative 0.5. Those are the two solutions from between 0 and 360 that are able to satisfy that equation. Notice that I've not included 30 because it's a negative, because sine 30 gives us a positive 1 over 2, but we're instead still using it as a reference angle to get the solutions from the other quadrants. Now again, using the same equation, I'll explain another concept now of double angle. What if I said sine 2 of x is equal to negative 1 over 2? How do you answer that? Maybe can you say positive 1 over 2? How can you handle that? So of course it will be the same. Sine inverse of 2x of 1 over 2, of course we do understand one of the possible solutions is 30. It's the one that's able to give us a positive 1 over 2. Because this has gone the other side, you're using it as sine inverse of 1 over 2. So now if you go to the quadrants, in the quadrants, we said this is where our 30 is. Now we said in the other quadrant where you expect it to be positive, where you expect something to be positive, it's in the second quadrant, which is 180 minus that, which is gives us 150. So 150 is also one of the other solutions. Now the fact that we have 1 over 2, we can still go beyond and rotate. So how do you get to find another angle? which is positive. You can rotate again, even reach up to 30. So if you reach up to 30, you've rotated 360 degrees. So you'd have to add 360 to 30, which is going to be 360 plus 30 is 390. And then you can also add to 150, add 360 to 150 if you want. Now this applies even if you have a 4 what and what. I'm just trying to show that you can even have 6x there. So the final answer, they'll give you a domain between 0 and 360. So you now begin to divide by 2, by 2, by 2, by 2, by 2. So you now have your x being equal to 15 degrees as one of the possible solutions, 75 degrees to be one of the possible solutions. I don't know how 390 if you divide by 2. So you get a 90. What? Of course 20 gives 40, so 19. Oh, what's that? Yes, into 3 it's 2, it's 1. And then there it's 4 times a remainder of a 1, so 145 degrees. And then it's 145. Is it 145? It's not 145. I'll repeat that. 2 into 3, it's 1, carry 1. Into 19, it's 9 times, carry 1. So 195 degrees. And then that is 180 plus 75. That's likely to be 5. 16. So it should be 265 degrees. So these are the possible solutions less than 360 degrees that you can satisfy that equation. That's how we basically get under them. Okay. What else do we need to undo now? Now the other aspect that I need to remind you of that we learned about under solving of trigonometric equations is the aspect of you using the special triangles. Of course, the 1/2 is common and whatnot. What if I brought to your attention, let's say, sine of x is equal to negative root of 3/2. So this triangle, if you know special triangles, you'd have to think of now the 60/30, right? 60/30. This is where the 1/2 comes from. So you understand, first of all, it's a right angle triangle. That is 30, that is 60. Okay, so sine 30 is 1/2. So what tells us sine opposite over hypotenuse. The other side becomes root of 3 using Pythagoras theorem. So if you try to think of it, what sine value can give you negative, in fact, a positive root of 3/2, because we use that as, so obviously it's going to be 60, because you understand that if you use 60 there, its opposite is root 3, the hypotenuse is 2, so it will be 60 as your reference angle. Now you ask yourself, where do I expect my sine to be negative? It's in the third and fourth quadrant. So in the third quadrant, we said you add to 180. So 180 plus 60, it will be 240 degrees. And then of course in the other quadrant, in the fourth, subtract from 360, it will give you 300 degrees. Okay, so continue from where we ended in the previous video. Now consider a case where you have cosine 2x is equal to 1/√2. So are you able to remember the triangle that deals with √2? Do you know that triangle? Are you able to write it down and use it? So it's 45, 45. That triangle basically tells us what we're supposed to deal with. So for the sake of that, I'll use radians in this video to answer so that you get acquainted with it as well. So of course that triangle tells us 45, 45 is something that is like this. The sides are equal, 45, 45. So it doesn't matter which one you take, to be the opposite. Of course, that's the hypotenuse giving us a √2, and then the sides are equal, both of equal length. Let's say 1, 1. So when I say try to use 45 to drive cos 45. Cos 45 will be 1 over root of 2, and then sin 45 as well is 1 over root of 2. That's why tan 45 is equal to 1, because of this very fact. So we now know the angle that is able to satisfy this equation. So 2x is going to be the cos inverse of 1 over root of 2, which is now going to be our 2x is equal to 45. Now I want to work with radians. 45 in radians is multiplied by pi over 180. Are we able to divide now? How many times can we divide the 45 into 180? In 290 is twice, so in 180 it's going to be 4 times. So we have pi over 4. 4 times, right? Good. So at that point, we need to understand where else do we expect our cosine to be positive, since it's a positive 1 over root of 2. So if you look at the 4 quadrants, we said all students take calculus. So where there's C, that's where cosine is positive. That's in the 4th quadrant. So in the 4th quadrant, 360 is the same as 2 pi. So it's supposed to be now be 2 pi minus pi over 4 as one of the possible solutions. And then you can add the solutions we have so far, which is 2 pi, add 2 pi to it. So add 2 pi to pi over 4. And then let's try to see first of what we're going to have. So we have 2x being equal to pi over 4. And then if you subtract 2 pi minus 4, 4 times 2 pi, that is 8, minus pi, we have 7 pi over 4. And then that is going to be 4 multiplied by 2 pi, that is 8 pi, and that is 9 pi over 4. So at this point, you can also add 2 pi to 7 pi over 4, provided it doesn't, but I think that's going to be too big though. Unless if we had maybe a 3 or a 4, we could have gone that far, but we'll end here. So at this point, to find the actual values of x that satisfy the equation, we'd have to divide by 2 now. So dividing by 2 is the same as multiplying by 1 over 2. So our values of x will be pi over 8, 7 pi over 8, 9 pi over 8. So these are possible solutions we have less than 360 degrees. Okay. Now the other thing that we've also learned in the series on how to solve our equations, we dealt with identities. So a basic identity was the sine squared of x plus the cosine squared of x is basically equal to a 1, right? So from there we tried dividing by cosine throughout. After dividing by cosine throughout, we saw that we basically got sec squared of x being equal to 1 plus tan squared of x as an identity. Okay, these are the two common identities we basically will get to work with. Of course, if you try to divide by sine squared of x as well, you get to have, of course, cosine divided by sine squared of x is cotangent squared of x, and then equal to the cosecant squared of x. These are the three identities usually used when it comes to the solving of equations using identities. So let's say, for example, you had a question, you need to find the values of x that satisfy this equation. So since we learned this under identities, pause the video and try this one out. So looking at this form, these are already matching up, so I would rather convert the sine squared of x. So I understand that if I make it the subject of that identity, it will be 1 minus cosine squared of x. And then I can now collect the like terms. So if it goes back the other side, it now be positive. So we have now 2 cos sine squared of x plus cosine of x. The 1 will become now a minus, equal to 0. So if we try to factorize this, at this point it's a quadratic function. So we'll have the product is of course a minus 2 understand, you multiply the coefficient of a and the constant c. The sum is the middle part, which is just a 1. So what two numbers can you multiply to give you a minus 2? You add them, they give you a 1. So it's obviously a 2 and a minus 1. So you can handle this like this. It will be 2 cos squared of x, and then the middle part is going to be substituted with 2 cosine of x and minus cosine of x minus a 1 equal to 0. So any factors we have 2 cosine of x for the first part, and then you remain with cosine of x, and then plus a 1. There you have a common factor of a minus 1, so you have cosine of x plus 1 equal to 0. So otherwise, what do we have now? So what we have is we have 2 cosine of x minus 1, and then we have cosine of x plus 1. So these are the two now equations that you can basically now use to simplify. So they are taking us back like to the basic equations we started with. So the first one is 2 cosine of x is equal to 1. The other one will be cosine of x. If it goes the other side, it becomes negative. So here it will be cosine of x is equal to 1 over 2. So even though the reference angle there is 60 degrees, of course, if you try to convert it, it will be pi over 3 in radians. Okay, so solve these two equations from the basics we've talked about, then you're home and dry.
Let's basically just get to understand how we get to graph our trigonometric functions as simple as possible. Okay, so this is our graph. This is what we have as our xy plane, and then of course we need to understand the basic forms of our different trigonometric functions. So to start with, we're going to first of all look at the sine graph. Okay, so how does a basic sine graph come out on a graph? So if you get to graph the basic sine function, you do know that it's going to be something that is going to come out like this. Okay, and then it gets to end there. Okay, that's a basic form of the sine graph. And of course, we do expect that this is going to be 90, which is pi over 2 in radians. This is pi over 2, and then this is our pi, and this is 3 pi over 2, which is 270, and then finally we have 2 pi, which is like 360 in degrees. So this is a basic form of our sine graph. Okay, so if you know the basic form of a graph, it's going to be very easy for you to sketch a graph. Okay, whether we've added things like the amplitude, the phase shift, the vertical shift, all these things are just going to have a slight effect on the basic form of a function. For example, what if we try to say sketch sine, okay, let me start with 4 sine, and then I'll say 4 sine x. So what you need to understand is the 4 that is indicated there is what we call the amplitude. So basically the amplitude tells us how high the graph is going to go and how low it's going to go. So of course in this case I needed to indicate that it was going to be a 1 and also a negative 1 to be our minimum y value. Why? Because the basic form of a function just has a 1 there. So in a case where we get to have a 4, what is going to be easy? We can just, no need of us even getting to worry about that. We can just change here and then show to say we have positive 4 and also a minus 4. So we now understand the effect of the amplitude on our graph. What about if we try to change something else? Let's say if we said we have 4 sine and then 2x. So now you understand that this is 2x and then that is x. So this takes us to a new effect, which is we are calling the period. Okay, so the period is also one of the things that gets to affect the basic function. And how does the period affect? So it's denoted by capital letter T, and of course it's dependent on the coefficient of x. Okay, so in this case we have a 2. So the period is basically determined or calculated using this formula where we say our period is equal to
So say 2 pi divided by the value, of course, the absolute value of b, which is the coefficient of our x. So in this case, in the initial form, we just add a value of a 1 being the coefficient of x. Okay, so therefore our period is just 2 pi, and of course we do understand what the period is. This is like how long it's going to take to complete a revolution. So if we are starting at this point, how long is it going to, like in terms of the x-axis, we need to complete a full cycle. Okay, so we need to have the crescent as well as, so we need to have the top part as well as the bottom part. Okay, so and then we are going to get to the initial point. That is what we're calling the period. So from this point where we're starting up to the ending point for a complete wave, full wave, that's what we're calling our period. Okay, now what happens if we have a value of 2, like in this other case where we're saying 4 sine 2x? So that would mean that we, in our calculation there, we would need to divide by a 2. So if you divide by a 2, what do you expect to have? You're basically going to have pi, which tells us to say that we need to have a complete revolution within pi. So therefore, if we sketch our graph on this same scale that we have, what we need to expect is we need to have something that is going to come out like this. Okay, so it would have to come out like this. Okay, so the basic idea is, what we are noticing is there's a complete revolution within just what? A pi. And of course that's what it means. But to make things easier, what we can do is we can do this. I'll erase everything, and then we'll just try to make it smoother. Okay, so this is our graph. So the only basic idea is, since our period in this case from this graph is giving us a pi, we can just make our lives easy by just what? By just, of course, drawing the function itself, of which we do know is this is the way it's going to come out, the normal way. Okay, now since we know that our period in this case is pi, instead of putting 2 pi at the end as we do for the basic form, it's going to change. We'll just change and put what? We'll just put our pi there. Okay, so we know this is the middle point. So what's the half of pi? It's going to be pi over 2. And then of course, what's the half of pi? Pi over 2. It's going to be pi over 4. Not so. And then of course you need to find the middle part between pi over 2 and also pi. So pi over 2 plus pi. This is obviously going to give us so that is going to be 3 pi over 2. And then if you get to divide it by 2, it's going to give us 3 pi over 4. Okay, so this is basically what we have on our graph. Okay, so that is the effect of the period on the graph. It basically changes the complete revolution where it's going to end on our x-axis in terms of our angles. Okay, so we now know the effect of the amplitude as well as the period on our graph. Okay, what if we tried to add something new? Let's say the way the graph is 4 sine 2x, and then what if I get to, let's say, maybe add something, maybe add pi. Okay, how do you expect this to be different? And of course, to just make it interesting, I can put this in brackets, and then let's say that's what we have. So the pi that we're seeing there is what we get to call phase shift. Okay, so we now have, first of all, we do have the basic form of that graph. Of course, looking at it in the case where it is having a period of a pi, I'll not alter anything, I'll leave it the way it is. Let's try to understand the way the phase shift is going to affect this graph that we already have. Okay, so the phase shift basically shifts the graph along the x-axis. Okay, and of course, every time you have that form, you need to make sure that every time you're trying to sketch a graph, you need to have the 2 factorized. It should be outside the brackets. So therefore, if I get to factorize out my 2 there, what I expect to have is our 4 sine, and then the 2 is going to be outside, and then I'll remain with x. And of course, from our factorization, we are taught to say that it will become pi over 2. The basic idea is if you get to distribute the 2 inside the brackets, you should be able to get what you had initially. And of course, if you multiply 2 by pi over 2, you expect to go back to the original form, which is going to be 2x plus pi in the brackets. Okay, so this is the value of a, that's our value of b, and then that is now our value of c. So the value of a helps us to determine our I, which is the amplitude, and how low it's going to be, as we can see on our graph. And then the value of b helps us to determine the period, which is telling us the angles that is going to take for it to complete a wave. And then of course c is giving us a phase shift and how we are going to shift along the x-axis. And of course, every time it's positive in the brackets, what we need to expect is it's supposed to go towards the left hand side, and it's negative, supposed to shift towards the right hand side. So in this case where it is positive, or if you don't want to master that, what you can just do is always just equate what is in brackets to 0. So it's basically going to be our x being equal to negative pi over 2 if you equate what is in the brackets to 0. So therefore, that basically signifies or indicates to us that we're supposed to shift towards the negative by a magnitude of what? Pi over 2. So each point that we are seeing on the graph, I'm now free to erase this for a moment. And then of course, just take note that our graph is now 4 sine. You can just write that 4 sine 2x, sorry, supposed to factorize it 2, so that is x minus plus pi over 2. Okay, that's our graph that we have in the simplified form. And of course, what we are saying is if this is a phase shift, that is our phase shift, so our graph is expected to move towards the left hand side. So this point is supposed to move by a magnitude of what? Pi over 2 to the left. So I'll just indicate using the scale that we have. So of course it's going to be pi over 4, and then that is going to be like pi over 2, and of course these are negative values, so I'll put negatives. So therefore this point will now shift to that point, and then of course whichever point, that point will also have to shift by negative pi over 2. And the easiest way of you doing that is if you look at the way I've used the scale that we have, depending on the graph that we have, this point has moved like 1, 2, so it's just skipped 1 point. So even this one will just have to skip 1 point so that it will go to this point. And then this point also just skip 1 so that it will come now to this point. And then this point will also just have to skip 1 point. So if it skips this one, it will now be at this point. Okay. And then of course the last one will also just skip 1 and then get to this point. So if we get to sketch the new graph, it's going to be something that is going to come out like this. So this is the confusion that we have. Let's try to see how we've moved this. Okay, this is something that, okay, so I'll draw that again, and then passes there, and then there. So we can even continue. We've seen the way it's moving, so it will have to move again to that point, and then finally it gets to that point. Okay, so that is the way you need to understand that. That's the way phase shift is going to affect our graph. And of course, if it is, we are specifying the domain. If you've discredited the negative part, you can just put dotted this side so that you show that the actual graph is starting from 0. But for the sake of helping you to sketch it, you can just show it to see the way. Okay, this is the way the graph has moved, but what you need is just this part. Okay, so we will specify, of course, the domain that they're interested in, but basically that's how we can talk about the effect of the phase shift on our graph. Okay, so we now understand the effect of the phase shift on graphs. Now we also need to understand the effect of the vertical shift. Okay, so going back to the basic form of our equation, where we said y is equal to sine x. This was the basic form of the equation. Okay, from there we had to understand the effect of the amplitude, where we said this is going to be 4 sine of what? 4 sine x. So what did we see? So if I go back to the graph, let's go back to the graph. So this was our graph. Okay, so we saw to say whenever we are talking about the sine graph, something that is going to come out like this. Okay, that is the basic form of the graph. So the amplitude had to change the value from a 1 to 4, minus 4. That was the effect of the amplitude. And then of course, in the normal case, we do expect the basic form of the graph to have a period of what? To have a period of 2 pi. But again, after changing the coefficient of x, where we say 4 sine 2x, we saw to say these two as an effect on the period, which would determine where the graph is going to end. And of course, in this case, you have to be pi. Okay. So of course, it doesn't necessarily mean that you're supposed to end on the period, but what it tells you is it tells you to say within that's where you expect the graph to be complete. So there may be some cases where you have a period of pi, as we can see in this case, and then of course they tell you to say you need to draw from 0 all the way up to 2 pi. So in that case, that would mean you need to have two complete waves made. What's that supposed to mean? What it means is this. So you're moving from 0, and then of course, let's say you consider the last part to be 2 pi, and then your period is like pi, not so. So what you'd expect in that case is you need to have a graph that is going to be something like this. So this means you have the full form of a graph, two of them formed. So there is this one, complete within a pi. So we'll call the middle part to be our pi. So that's like our pi. And then again from pi to 2 pi, there's also another complete wave, starting at this point and ending at that point. So that is the basic idea of the effect of the period on the graph. We've also talked about the effect of the phase shift, where we said if let's say you have minus pi over 2, or let's say positive, when it's positive it's supposed to move towards the left. So each point is supposed to move by that very magnitude shown. Okay, so it will move, each point will move, and then you need to draw the new graph just that way. And then now let's try to understand now the effect of what we're calling the vertical shift. So I'll write the same form of our equation that we've been talking about, and then I'll of course work with x, that's a period of 2 pi, and then we'll say, let's say we had 4 sine x, and then let's say we had plus 2. Okay, so I've made it easy so that we just get to see what's going to happen. This is a basic form of equation. It can also be negative. Okay, so what's the main idea there? And of course, I can even add it this side so that you are not confused with the phase shift. So this is a vertical shift. This one gets to affect the y-axis, just like you might guess. Okay, so looking at the graph, so of course if you look at our basic form of the graph that we have in this case, I'll draw it. Okay, so the amplitude is basically 4, so I'll put the 4 and also minus 4 there. And then of course our period is 2 pi because value of the coefficient of x is a 1, so we're ending at 2 pi. So this is our pi, this is like pi over 2, and then this is like 3 pi over 2. Okay, what are we trying to say? What is going to be the effect of the 2 there? So just like we are coding it, we're coding it the vertical shift. So it's going to shift the graph in terms of the y-axis. Okay, so each point is going to go up by 2. So if you want to make things easier again, you can just start moving each point by 2. So if this is 0, of course, if you move it by 2, where do you expect it to go? To go to 2. So now that has moved to 2. You can move this point as well by 2, it will go to 6. You can move this point as well by 2, it will go to 2. This point by 2, it will go to -2. And then the last point from 0 as well, it will go at that point. So if you get to join all these points, this is basically what you're going to have. Something like this. And then, so what have we noticed? So each point has gone up by 2 because of the vertical shift. So it's also possible that this can be a negative, which will tell us to say all the values in the y are going to reduce by 2. Okay. So now, if you don't want to do that kind of shifting, what you can do is just move the 0 line to what? To the actual vertical shift that you have. So if you have a 2 being your vertical shift, what you can just do is just let 2 be what? The 0 line. That's all. If you consider that one to be the 0 line, basically you come up with the same graph. How? You consider the amplitude of 4. So if you're at 2 as your 0 line, and then you had a 2, you had a 4, sorry, which is the amplitude in this case, it will give us a maximum of 6. And then if you subtract by 4, it will give you a minimum of what? A -2. So you'll be able to say, okay, so considering 2 to be my 0 line, my maximum value is going to be a 6, my minimum value is going to be a -2, and then you just draw the basic form of the equation. Those are the two ways in which you can get to show the effect of the vertical shift on our graph. Okay, so now let's try to proceed and then talk about the cosine function. So what is a cosine function? So even just maybe before we get to talk about the cosine function, I think I'll just need to mention one thing about the sine function. What if in a case we give you negative sine of x? Do you expect it to be in the same form? Of course, the basic form of our positive sine function, just like we had shown, this is going to be something that is going to come out this way. Let me draw something bigger. So this is a positive sine graph. Okay, so positive sine graph, sine x, and then of course in this case we have 2 pi as our period. That is like pi. I think these points are enough. And then of course we have 1 and also a -1 as our amplitude. Now what about if we said negative sine of x? And of course these values can be determined on your calculator. If you are even allowed to use calculator, it's even easy as well. So all you can do is, if you try, of course this is pi over 2, your calculator is supposed to be in radians, of course. Okay, so that is pi over 2, and then this is like 3 pi over 2. So in degrees, of course, this is 90, that is 180, that is 270, and then that is like 360. You can also use those values depending on what you are using on a calculator. Okay, so now what happens if you get to say negative sine of that? So remember, this negative is going to affect the value of y, and what it tells you to say all the values that you have for the sine graph are supposed to be regarded as negatives. So that is going to be more like a reflection. Every positive value is going to become a negative, so only the 0 line is going to be maintained, and therefore this positive value, because of a minus that is there, is going to be reflected to the negative part. 0 values will not change. And then of course this is a negative, so if we multiply by a negative, it will become a positive. So these are the 2 points that are going to shift, and therefore that's why the negative sine graph is something that is faces like that. Okay, it is kind of a reflection of the actual graph. So for it, it's going to, instead of starting upward like this, is to start from the bottom and then end with the top part. This is what we call the negative sine graph. And of course, in a case where they get to put things like -4 sine x, all the same, all the things are going to apply, but just know that instead of starting with the top part, you start with the bottom part. And that is how the negative sine graph is different from the actual positive sine graph. Okay. So of course, also we need to understand now the cosine graph. So how do you basically show the basic cosine graph? So our cosine graph, let me just draw. So our cosine graph is something that is going to come out like this. So it has to start from that point. Maybe let me draw something better. Okay, I think that's better. So, and then this is too small. I can do this. Then I can sketch. I can put something like this. Then I can put it there. Then I'll put it there. Okay, now I can now draw. So remember, this is not a line. It's like it's supposed to be curved. So that is the basic form of a cosine graph. So if we're saying this is a basic form of a cosine graph, of course we are considering cosine of x. So considering the cosine of x, we are starting at also the amplitude of the 1. So everything else relating to the amplitude, the phase shift, the vertical shift remains the same. All what is important is for you to understand the basic form of the graph. So of course this is going to be our pi. This is like pi over 2. That is like 3 pi over 2. And of course the last part is 2 pi. So this is the way the cosine graph comes out. And of course if you talk about the negative form of it as well, you expect that it will behave more like a refraction. So that it starts from the bottom part and then ends at that point and then it gets to come down again. Okay, this one is the negative cosine graph. So just you knowing the basic form of the graph will allow you to basically apply the effects of the amplitude, the phase shift, the vertical shift, and also the period. Okay, so what happens if we get to consider cosine of 2x? So you feel free to try that one out from the basic understanding of what the period is. So of course we said our period is going to be dependent, and also to make it interesting I can also add an amplitude of 2, so that we have 2 cosine 2x. So our period is basically expected to be 2 pi divided by the value of our b, which is the coefficient of x. Okay, so this is going to be what? Going to be pi. So going to our graph, okay, so what I told you to say is what you can just do is just consider the basic form. Just draw it, just draw the shape of the graph itself. So this is the expected form of the graph. So all you can just change is let the ending point be what? Be pi. That's all. And then you can divide it into half, which is going to give you pi over 2. Divide pi over 2 into half will give you pi over 4. And this is of course going to be 3 pi over 4. Okay, at that point. So that's how you sketch it. And then if I've told you to say it's a graph that you expect to end at 2 pi, you can extend it, of course. You can extend it. How do you get to extend it? So it will continue moving just as it is. So look at the way it is. Look at the way it's behaving. So you expect it to go down. This side you expect it to go down as well. Because one thing that you're noticing is the fact that this is basically our amplitude. Okay, so in this case the value is what? It's a positive 2, and then on the bottom it's a minus 2. Okay, so that is the way you expect this graph to basically behave as a cosine graph. And in a case where you have a negative, if we had a negative all that, or what is going to be different is going to start something like that. So let me put this point there. I mean, to just be something like this. Yeah. So it can be it will continue moving like that. Yeah. So it will behave depending on the way it has started moving, and that's the basic idea of this graph. Okay. So I think this point we can make it better if you want it to. Yeah. If you are continuing up to the point where we say 2 pi, you have to extend it more curved. Okay. Anyway, so what is the basic form of the cosine function, and that's how it gets to work. So of course, with the additions of multiple things, it will make more sense when you have a phase, you have a phase shift, vertical shift. All those things are going to apply the same way we talked about the sine graph. Okay, so I think this is where we get to end in this video, and of course, feel free to register using the link below to access the solutions to those different graphs that are shown in the tutorial sheet for Math 1100, Math 1120. Okay, you'll be able to access those solutions. So I just basically hope that you now have a basic understanding on how to go about the graphing of trigonometry. Okay, so if you're actually enjoying this video, you can actually have access to the full trigonometric solutions that will allow you to understand the topic fully. So the question 1 is there, the question 2 is there, the question 3 there, the question 4, identities are also there. As you can see, questions 6 and 7 are based on identities. Double angles are also there. Okay, so you'll be able to understand the half angle principles as well, looking at question 4. And then as we go to question 8, you also be able to understand how to go about it, how to solve trigonometric equations. Question 9 is also there, how to answer more equations. Question 10, dealing with sketching. Question 11, dealing with sketching. Question 12, dealing with sketching. Question 13, sketching as well. And then you also understand how to determine or evaluate these trigonometric kind of expressions, looking at question 14, 15, and also 16 as well. So you can have access to all these solutions by just registering. So you can visit our site, the link is in the description. From there you can also learn the topic from scratch, each basic concept step by step, and also access the solutions to this entire tutorial sheet. Metric functions. You have a lovely day. We've not talked about how to sketch the tangent, so I'll explain how to sketch the tangent graph just here, so that you basically get to have an idea. So one thing that I want you to know is each time you have what we call asymptotes, okay, these ones are going to be the vertical asymptotes. Are they vertical asymptotes or okay, yeah. So if you've got asymptotes like that, and then you have a 0 point somewhere, let's say here, the way you expect that graph to behave is like this. Okay, or if you've got a 0 point somewhere there are two ways the graph is expected to behave, either this way for the tangent or this way. So I'll be able to tell how. Okay, so what it means here is the values of y are never ending. Okay, so infinite. Now let's try to understand the way the graph actually gets to behave. So if you have the normal tan function, tan x, the idea I can give you is the simplest way of sketching this graph is just put your negative pi over 2 somewhere there, and then your pi over 2 somewhere there. Okay, come up with the asymptote as pi over 2 and also So why am I saying so? I'm saying so because you know that that point there is 0, tan of 0. Now you know that tan is the same as sine divided by cosine. So it's the same as sine 0 over cosine of 0. Now sine of 0 is equal to a 0. Cosine of 0 is equal to a 1. So 0 divided by 1 is 0. So that is a possible 0 point. Now, as you go to tan 45, tan 45 is a case where we said cosine and sine are equal. So that is equal to a 1. I hope now you're getting the basic idea there. So tan 45, which is of course somewhere here between pi over 2 is a 90, so somewhere there it's equal to like a 1. Okay, so what means is the graph going that side is going like that. Okay, and then as we go the other side, it's going like that down. So this will continue happening now. So when do we again expect the graph to be equal to a 0 or tan to be equal to 0? So the only way you can have a 0 in this kind of a graph is okay, let's assume we don't know. Well, we know that the next part will be pi, the next part will be 3 pi over 2. So how do we know the behavior of a function at that point? So if we get pi, tan of pi is going to be sine pi over cosine of pi. Now sine 180 is what? It's a 0. Cosine of pi is going to be what? That is a 1. Is that a 1 or negative 1? Something like that. Anyway, if you go to the graph, go back to the graph of a cosine. So it's a negative 1. So despite it being a negative 1, you still get a 0 because the numerator is a 0. So this is another 0 possible point. Okay. So how do we expect the graph to behave? So it will behave the same way. So even that one will be the asymptote there. So it will continue behaving that way. So it's going to start from there and cut there again like that. So you've seen that within the diameter or within the domain of pi, this is the way tangent is actually behaving there. Okay, this is the way it is behaving. So I can actually start by answering the the second part of the question. So the second one says we need to find we need to sketch negative tan. So the first thing that you need to notice is the negative part. So that negative sign is changing whatever the way the graph is behaving. So it will instead start from there and come like this, again like that. So it's like a reflection again. Okay. Now the other thing that is also affecting the graph is the aspect of what? That is we've got a pi attached to x, so it's going to affect the period. So the period is of course going to be 2 pi divided by that value, which is pi, giving us so a pi will go away and then you remain basically with just a 2. Okay, so therefore to avoid confusing yourself, I would advise you just like remove a pi to whatever values we have there and sketch it the normal way. So we'll do this. I want it to be as simple as it possibly can be. So this is going to be negative pi over 2. This is going to be pi. So I already told you to say in the normal way expect it to come like this. Now the fact that we've got a negative, it means the negative values will become positive and vice versa. So the graph will instead come from that other side like this. Okay. So of course take note of the asymptotes, clear to show the asymptotes. The graph should never cut the asymptotes. Okay. So that is at pi over 2. So of course in most of the cases they're not interested on the negative part, so that's where the graph comes out like that. but I'm just trying to show you for the sake of understanding. Now that is in a normal way, okay? That is in a normal way where we just don't have that pi attached there. Now the fact that it is attached, it is having an effect on the period. Instead of the period just being 2 pi, the period is going to be 2. Okay, so how are we going to take that? So remove the pi so that we see what's going to happen to the graph. So it's going to be something that is going to be more like, so we'll have, instead of pi over 2, we'll have half, and again we'll have a 1 instead of pi, and then we'll have 3 pi over 2, so it's just a 3 over 2, and then we have a 2 there. So of course we know within a value of like a 1, we're supposed to have that full kind of a graph. So the other asymptote will occur at 3 pi over 2. So the graph again will come in the same way. I don't want it to, so like that, going up, going down, and then again start from there again and just cut at 2. That's the way it's going to end. So that is the way the graph has behaved there. That's the way we've sketched the negative tan. So negative tan pi over x, pi x. So the question was saying we need to clearly state the period. So a period in this case is a 2. I've shown you how to calculate. The amplitude is where the graph is expected to end. Now we've seen that you've got asymptote, so the amplitude is just going up, so it's just infinite. And then the phase shift, did we have any phase shift in this case? No, we didn't have any phase shift. The graph has not shifted. And then did we have any vertical shift? No. So yes, that's 0, 0, and 0. Only taking note of the period to be a 2. The amplitude is infinite. So with all these ideas of how to go about the sketching of a tangent function, I can confidently take you back to the first part of the question. So there we have y is equal to cotangent to x. So that's what we need to sketch there. So how do we understand the behavior of that cotangent function? How do we expect it to possibly behave as we sketch it? What do you think is going to have an effect on that graph? So one way you can think of that graph is take it to be, assume it's just tangent of 2 of x. How do we sketch it? Remember the way we are from sketching the normal one is, let me show the asymptotes again. So remember, if that is 0, this is going to be pi over 2. We'll have pi in between, and then we'll have 3 pi over 2, and then we'll have 2 pi in between there. So in case you are forgetting where the asymptotes are, just ask yourself, remember tan is the same as sine over cosine, right? So just ask yourself where sine is equal to 0. So you've noticed that sine is actually equal to 0 if you draw the graph at 3 identical points, at 0, at 180, and also at 2 pi. Sine is equal to 0. So those are the points where you expect the graph to exist. So it's at 0, pi, and 2 pi. So this part we say the graph starts like that, right? Okay, and then at this point it also start like that and go down there, even there. So even there we also expect the same. Now in the case where we're ending at 2 pi, this other part is like removed. Okay, so it comes out like that. So this is with a normal period of 2 pi radians. Now in this case where they're giving us we have got a 2 attached to the value of x, meaning that we need to divide the 2 pi by the 2, giving us now giving us a period of pi, meaning that the graph is supposed to be complete within pi. So all these are supposed to be indicated within pi. So one way of acting smart is by thinking of it in this way. So since we're ending at 2 pi, if we're ending at 2 pi, this part of course does not exist. So you can just remove, to avoid confusions and just avoid losing yourself, just remove those values there, and just know that the last point is supposed to exist at pi, and then divide by 2 so that you go back to the half point where you're at. So it's going to be pi over 2 there, and then again divide by 2, it will be pi over 4. Add pi and pi over 2, of course they'll give you 3 pi over 2 divided by 2 to be 3 pi over 4. Yeah, I think I'm trying to give you, I don't know if I think people might actually call it Cook's method. Yeah, but it works. It works. Yeah, it is definitely going to work. So this is the way you expect the tan of 2x graph to basically get to come out. Now in our question, they want us to find cotangent of 2x. Now cotangent is the same as 1 over tan of 2x. Now what does that mean? What does that mean? So this is actually, what this means is you actually have the reciprocal of the actual graph. The reciprocal of the actual graph that we have is the expected result or solution to the graph. So how are we going to sketch the graph now? So if it's a reciprocal, it means the values are going to be the opposite. These values that are high will be lower, and so on and so forth. So how is it going to come out? So we can actually try to picture what we're trying to say here. When we have the values of tan, let's take some few values of x. So x, and then we have tan of x. Okay, let's take a few ones. 0, pi over 2, and pi. So you know that tan 0 is what? Sine 0 over cosine of 0. So sine 0 is a 0, so that's going to be a 0. As the graph even tells there, tan like of pi over 2, that's like sine 90 over cosine 90. Cosine 90 is a 0, so that is undefined. And then tan sine 180 will be a 0, so that is going to be a 0. So now you know that where the vertical at, where the vertical asymptotes are going to be occurring is where the graph does not exist. So like in the normal case, it's supposed to occur at pi over 2. Okay, now in this case, if we introduce now cotangent of x, which is going to be like the opposite, which is going to have like cosine of x over sine of x. In such a case, we are trying to avoid the parts where sine is equal to 0. So it will be the opposite So what does that mean in reality? What that means in reality, if we look at the graphing that we expect, if we have, let me try to show you part of the graph. So if we expected our graph to come out like this, I'll take these 2 points, 0, pi over 2, and pi. So we know that 0 is where the graph is there. So we expect the graph to come out like this, right? Because pi over 2 is an asymptote in the tangent function. Again, pi is a 0 point. Of course, the next tangent will be 3 pi over 2. So the graph here is also expected to be something like this. Something like that, right? This is what we are expecting and we are seeing, noticing there. Now, if we introduce a cotangent, the cotangent we are saying it is basically the opposite. So where we have a 0, it becomes asymptote. Okay? Because of what we are saying, there is a dash there. And then where else do we have an asymptote? We also have an asymptote at pi. So here is also another asymptote. So how do we expect the graph to actually basically move? If that is the case, is it going to start like that and come like this, or it will be the other way around? So we know, of course, pi over 2 will give us a 0, meaning it will be there. Now what happens if you basically get to try cotangent of a certain value? Is it going to be above the x-axis or below the x-axis? For argument's sake, we can get the other way of basically getting to reason about it is asking yourself where tangent is positive. So all students take coffee. All students take coffee. So if you're after pi over 2, and then of course that is happening between pi 0 and pi, 0 and pi. So and then you're after pi over 2. At pi over 2 it's 0. Now as you go into this other quadrant before pi, it is going to be negative, meaning that it will be below the x-axis. So it is expected to move like this. So here it will be above, and then there it will be below. Okay, so this actually gives the basic idea or a basic sense of what we're trying to say here. So actually I never even thought of this, but this is one way we can actually think of it. So don't forget that this graph that we have on the left is a graph of tan of 2x. So I was just trying to show you the basic idea. So cotangent of 2x, as I've showed you to say there's a difference, cotangent will be like the opposite. So the graph will be expected to actually start from here. Start from there. So the 0 points will now be the 45. So here the 0 point will be this point. The 0 point there will be at that asymptote, and then the graph will move like this. So it will be like that, and then get to, it's actually pi over 2. Pi over 2 like that. Okay, so that will be asymptote, and then again it will move like that, cut that point, and like that. So you're seeing the kind of reflection that we have. And then overall, the graph we're having after reciprocal is something that has come out like this. Not so good. Again. then we have an asymptote here, another asymptote here. So this is pi over 2. That is occurring at that's occurring at what? 180. So pi. Wait. I hope I'm not losing you again. It's actually 3 pi over 4. Yeah, anyway, let me remove the unwanted parts. This is unwanted. So this is the actual graph that is required, the red one. Yeah, I'm sure you get the basic idea there. So the basic idea is know the basic tangent function, which of course starts like this. Better thought of to be, let me just try to summarize everything here. So a tangent function, better thought of to be a graph that starts from so you know that the tangent graph is going to be equal to 0 at a point where sine is equal to 0. So where are those points where sine is equal to 0? So if you draw the sine graph, the parts where it cuts to 0 is 0 at 0 so at 0, and then at pi, and also 2 pi. So pi and also 2 pi. So those are the points where we expect there. So let's try to now show it in summary. So we have 0, we have pi over 2, we have pi, we have 3 pi over 2, and then we have 2 pi. Now, know your quadrants as well to help you understand. Know your quadrants. So the points where where sine is equal to 0, those are the points where the graph will actually be cutting the x-axis. Now, the other points where cosine is 0, those will be the asymptotes now. Those will be the asymptotes. So this is, of course, asymptotes are supposed to be dotted. Just bear with me, they are not going to be dotted. So that is an asymptote. Now, all students take coffee. All students take coffee. So remaining that's the thing I should remind us of quadrants. All students take coffee. So you ask yourself, do you expect the tangent graph to be positive or negative in the first quadrant? So in the first quadrant, all are positive. So the graph will come like this. Now in the second quadrant, only sine is positive, so tangent will be negative. So here it will become from below, and there it will go up like that. And it is true actually, as you can see, in the third quadrant it's positive, so here it is positive, here it's negative, there it is positive. And then finally again, in the last quadrant it's going to be negative, so it will come like this again. So this is negative. So that is how you can easily sketch the tangent graph, by using the quadrants and understanding where it is positive or negative, and using and identifying the asymptotes. Now if I take you back to the cotangent, the cotangent it is actually the opposite. So how do you basically easily get to sketch it as well? So you can easily sketch the cotangent in this way. The cotangent is the opposite of tangent, so it's going to be cosine of x over sine of x. So this is going to be equal to 0 in a case where cosine of x is equal to 0. So where is cosine of x equal to 0? So if you draw the cosine graph, starts from there. So the parts where it cuts x-axis are pi over 2 and 3 pi over 2. So pi over 2 and 3 pi over 2. Pi over 2 and 3 pi over 2. So these are bites where it is expected to be equal to 0. So the other parts where sine is equal to 0, expected to be 0, pi, 2 pi, those will be now the asymptotes in this case. Of course, asymptotes are supposed to be dotted lines. Bear with me again, I'll just draw the lines. So these will be the asymptotes for the cotangent function, like that. Now ask yourself again. So where is, where do you expect, so in the first quadrant, of course, you expect that they are all positives. Just reduce the volume a bit. So in the first quadrant, they're all positive. In the second quadrant, sine is positive. And then the third, tangent is positive. In the fourth, you have cosine being positive. So that being the case there, in the first quadrant, they're all positive. So where do you expect it to be? So it's between 0 and pi over 2. So the graph, that being the asymptote, it will move like this. Let me use a different color there. And cut the 0 there. And then it's of course expected to be negative in the second quadrant. Okay. Again, here to be positive. This is the third quadrant. So that's why I'm drawing the cotangent for graph. Yeah. And then what basically happens after, now if we just, this being the cotangent graph, now if we introduce the 2x there, after introducing the 2x, the 2x makes it to be, you can now remove where there's 2 pi, like just remove the angles and just put, like at the last point you put the same new period that you're going to have, which is going to be of course pi. Okay, because 2 divided into 2 pi, it will just be pi, and then start cutting it into half. So it will be first of all pi over 2 there, it will be pi over 4 there, add 2 pi and pi over 2, 3 pi over 2, so it will be 3 pi over, is it 4? Yeah, so this is basically how we can easily sketch it the fastest way. Of course, it took time for us to just get to this summary. So from our previous video, we've talked about double angle formula. So how about half angle formula? How can we handle it? So with this understanding, we did talk about if you say sine of 2x is, we said that is equivalent to 2 sine x cosine of x. Of course, this came from the sum formula, or the add formula, right? The addition formula, where you say sine of x plus x. So you understand that it's sine shares to be sine x cosine of x, and then again plus cosine of x sine x. Of course, in terms of we understand all that, we did that earlier on. So for us to derive the half angle formula, we'll just substitute where is x, or put half of x. Okay, half of x. So we'll say sine on both sides of the formula, we'll put half of x, which is x over 2, right? Again, we'll say 2 sine x over 2 cosine x over 2. So what are we going to observe? So on the left we have sine of x is equal to 2 sine x over 2 cosine x over 2. So what are we observing? So we are observing, it's like, since we have 2x there it is x and x. So if you put x there it will be half of x, half of x. That's what it means there. Okay, and I've shown that now. Now, this is one expression you may have to know. Now, usually what they want you to understand is how you basically get to find, let's say they ask you to find sine x over 2. How best can you handle such a question? That's what becomes more necessary and more demanding for you to basically understand how to deal with. So how can we do that? How best can we handle that? So at this point, now that we have the one for sine, let's try to derive one for cosine now. What do we expect to have? So understand what cosine is. I was using a term like it's selfish to just help us understand. So it was basically cos squared of x, because it was cos x, and then minus sin x. So that is also sine squared of x. So equally, if you try to plug in x over 2, you have cos of x is equal to, so cos squared of x over 2 minus sine squared x over 2. Okay, you can think of this in that way. Then the other thing you can also, you'd have to note is for tan. So if you have tan 2x, we said it was the addition on top, so 2 tan of x, and then on the bottom it was 1 minus tan squared of x. So if you plug in again the same x over 2, you're going to have tan x is equal to 2 tan x over 2. This is just a trend that we are seeing. It's like the x that is on the left hand side is supposed to be halved on the other side, as we are saying, supposed to be divided by 2. So we've come up with these three identities already, that I'm sure you've now understood how they've come about. So if you look at the two, how best can we basically utilize this to help us deal with something more interesting and better off, okay, to help us find the half angles? So I'll take you back to the one for cosine. So we said cosine of 2x is basically equivalent to, it was cosine squared of x. So okay, we'll now go for the one that is simpler, the one that we've derived now. Cosine of x, on the other side it is cosine squared of x over 2 minus sine squared of x over 2. So this one is going to help us derive the formulas for the angle half, for the half angle formula. Okay, so what do we expect here? So we understand that from our earlier identities, we said cosine squared is plus sine squared, we are giving us a 1. This identity, very important. So I'll apply it to what we have in this case. So whenever you add this is equal to 1. So we'll decide now to substitute. Where there is cosine squared, we'll make it the subject. So if we make it the subject, this one is supposed to go the other side to become 1 minus of it. So we have 1 minus sine squared of x over 2. And then of course not forgetting that we also have 1 which is already part of the formula on top, minus sine squared of x over 2. So this will now be 1 minus 2 sine squared of x over 2 cosine of x. So we're trying to come up with a formula to help us to find a half angle where you're given a normal size. So if it goes the other side, it now be 2 sine squared of x over 2 being equal to 1. The cosine will come this side, it will become negative. So we understand we can divide by 2. So divide by 2. Now we need to find the square root on both sides so that the square can go away. So the moment you do that, you have to add plus or minus the root of what is on the right hand side. So that is our result now. So we are seeing if you find the square root on the left hand side, you are going to remain with sine of half an angle is equal to plus or minus the square root of 1 minus cosine of x over a 2. So we use the same one to also derive for the cosine of an half angle. So we said we've already seen that cosine of x is equal to cos squared x over 2 minus sine squared x over 2. So here what we're going to do is we're going to substitute. Now we have is sine, we'll put the cosine. So we have cosine of x is equal to, this one is going to be maintained. Now we have a sine. What are we going to put? We'll put 1 minus. We're using the very identity where we are saying cos squared plus sine squared x, they are basically give us a 1. Okay, this is now awesome. Cosine of x is equal to cosine squared x over 2. It will be minus 1 and then plus cos squared x over 2. So all these things are very simple. We're just repeating the same things. So we now have cosine of x, and then you have 2 cosine squared of x over 2. Those are like terms. The 1 can go the other side. It will be plus a 1. What can we do to find, to make our half an angle to be the subject of the formula? So find the square root on both sides. So cosine of x over 2 is going to be plus or minus the square root of what is on the other side. Of course, there's need for us to divide by 2. Divide by 2. So we'll have cosine of x, or if you want you can start with 1, is still the same, over 2 plus or minus of it gives us cosine of an half an angle. Okay, that's the other half angle formula that you'd have to know. The third one, of course, is going to be dependent on the 2 that we've come up with. Remember, we've said for sine of half an angle, it's plus or minus the root of what? Are you able to remember what we derived there for sine? So it was 1 minus cosine of x divided by a 2. So now the division of a 2 is basically what is going to give us for tan. So if you divide the 2, tan x over 2 is basically going to be the division between the 2. So it will be sine a over 1 plus cosine of a, which is also equal to 1 minus cosine of A divided by sine of A, still the same. So these are the three half angle formulas that you need to acquaint yourself with. So they are all derived from the double angle formula. So if you understood the double angle formula, it's very easy for you to even understand all these. So in the next video, I'll give you some few practice questions that you can look at using the same. So we'll look at trig functions as algebraic expressions. How do we get to express, for example, this given trig expression as a function? How do you convert it to algebra without seeing any sign, any tan? That's exactly what we want to do in this video. Okay, so I'll give us an understanding first of all, a basic introduction using the triangle that I have on my left hand side. This triangle is having an angle theta, and then we'll call the opposite side to be x. Okay, and then let this adjacent side to this angle be 1. So we'll find an expression for tan. So tan theta, so we already talked about SOHCAHTOA. What does SOHCAHTOA tell us about tan? So SOHCAHTOA, the last part, TOA, is tan of theta, its opposite over its adjacent. So what's the opposite here? So the opposite in this case is the x in respect to the angle theta. So it's x. And then what's the adjacent? The adjacent is a 1. So tan theta is just equal to x. X divided by 1 is just x. So Pythagoras theorem, of course, tells us the square of these two adjacent sides is equal to the hypotenuse. So in this case, the hypotenuse is going to be the square root of x squared plus 1 squared, which is just like 1. So the basic idea there is c squared is equal to 1 squared plus x squared. So if you try to find c, you have to find the square root on both ends, which is 1 plus x squared, as I've shown there. Okay, so with this in mind, if we decide to simplify or find the exact value of theta, we know tan theta is equal to x. So theta is going to be the tan inverse. This is also where we solve these equations, right? So tan inverse of x. We have that in mind. Okay. So now that we understand all this, we are now ready to take it to another level by now applying it to solving of the questions that we had. Okay. So before we can answer this one, which looks complicated, I'll use x there. Okay, so before we can answer even that question, we understand that we said theta was equal to the tan inverse of what? The tan inverse of x. So for us to simplify that question, we'll just substitute now. We understand that the tan inverse of x is equal to just theta. So sine theta. So sine theta is going to be equal to what? So we understand according to SOHCAHTOA, sine is opposite over adjacent, right? So the opposite in this triangle is our x, and then the hypotenuse is the square root of x squared plus 1. That's what we have in this case, and that's how you basically get to apply the use of this triangle to help us simplify. So what if now it becomes a bit different, where it is not tan inverse of x? Let's say tan inverse of 3x as it was. How do you answer it in such a case? So all the same, so we'll change everything, but we'll maintain one side, which is the 1. We'll maintain it as it is. Now the other side, we'll have to put back our 3x. Okay, this part is supposed to match up with whatever you have. So that if you say your tan theta, which is of course supposed to be your opposite divided by the adjacent, which is still going to be 1 in this case. So in this case again, your theta is still going to be tan inverse of 3x. So equally we'll do the same. Now you have to notice now that the hypotenuse would have to change again. The hypotenuse is going to be the square root of the square of the two adjacent sides. So 3x squared is going to be 9x squared, and then 1 squared will just be a 1. So that's what we have. So sine theta now is going to be equal to, our opposite in this case is 3x, our hypotenuse is the square root of 9x squared plus 1. Okay, so at least now we have an idea of what we're supposed to do for us to basically get to simplify. Let me make it a bit more interesting. Let me try to make some alterations. What if we say instead of having the sign there, what if I said we have sec squared of it? How do we answer it? So all the same, it is going to be sec squared of what? Of x. Sorry, theta in this case. So now we understand that sec, we saw it as an identity which is like 1 over cosine, right? So this is the same as 1 over cosine squared of what? Of theta. Now what is cosine? Cosine from Sokatoa it is koa, soka. No, actually it's not soka, something like that, soka. So it's adjacent over hypotenuse. So it's 1 over, what's our adjacent? Our adjacent in this case is 1. And then what's our hypotenuse? It's the root of 9x squared plus 1. So the reciprocal of that will just give us what? 9x squared plus 1. Its square root. That's our answer. We can look at one more practice question. So what if they gave us cosec and then they say cubed and then of tan inverse of 5x? Are you able to answer this one now from whatever we've done? So we can pause the video and try that out. How? So the way it's going to work is this. Whatever is in the brackets is what is going to dictate our triangle that we're going to use. So I'll draw the triangle, like a right angle triangle, and then I would put my theta there. So I'll let its opposite be whatever is there, which is 5x, and then the adjacent will be a 1, so that our tan theta is thus equal to 5x over 1, which is just 5x, and then theta is going to be now tan inverse of 5x. So we can find the hypotenuse. It's going to be a square root of 5x squared is 25x squared plus a 1 squared, which is just the 1. We get that from Pythagoras theorem. So now on our next step, now we have cosec cubed of theta. Now cosecant is sine, right? So it's going to be sine cubed of theta. Now we understand that sine is the same as what? Sine is the same as opposite over adjacent. Opposite over sine theta soa, sokatoa. Sine theta is equal to opposite over hypotenuse. So the opposite in this triangle is what? Of that theta. Its opposite is 5x. Hypotenuse, root of 25 x squared plus 1. Now sine is cubed, so we'll raise everything to the power 3. So that will basically get to simplify to. So first of all, reciprocal is going to be whatever is on the bottom will go on top, 25x squared plus 1 to the power 3 divided by 5x to the power 3. So you multiply everything by itself 3 times. Okay. So if you simplify that, of course you understand that if you multiply that by itself twice, the square root will go away. So you have 25 x squared plus 1, and then in the brackets you remain with 1 more, which is like 25 x squared plus 1 over what is on the denominator. If you try to multiply by itself 3 times, 5 times 5 times 5, I should be 125. So that's how you simplify. So you've seen that all our answers are not having any trigonometric function. So that is how you change the trigonometric functions to algebraic expressions by using a triangle. Okay, very useful. So in some textbooks, this tan inverse may also be known as what? Is it arctan? Yes. So that's the way you're supposed to approach that. Just know that it's inverse. So come up with a triangle, find expressions to simplify and substitute. Understand the identities as well. They are also very useful and helpful. Okay. So if you're actually enjoying this video, you can actually have access to the full trigonometric solutions that will allow you to understand the topic fully. So the question 1 is there, the question 2 is there, the question 3 there, the question 4. Identities are also there. As you can see, question 6 and 7 are based on identities. Double angles are also there. Okay, so you'll be able to understand the half angle principles as well, looking at question 4. And then as we go to question 8, you'll also be able to understand how to go about it, how to solve trigonometric equations. Question 9 is also there, how to answer more equations. Question 10, dealing with sketching. Question 11, dealing with sketching. Question 12, dealing with sketching. Question 13, sketching as well. And then you also understand how to determine or evaluate these trigonometric kind of expressions, looking at question 14, 15, and also 16 as well. So you can have access to all these solutions by just registering. So you can visit our site, the link is in the description. From there you can also learn the topic from scratch, each basic concept step by step, and also access the solutions to this entire tutorial sheet.